Uh, okay, cool. I think, can everyone hear me? Just to sanity check. Good, I see some reactions. Okay, I think we can get started once I find my screen. Okay, excellent. Okay, so welcome to our last lecture of the semester. We've studied a lot of topics, and today we're going to conclude with virtual memory, and then we'll have an epilogue session where we will talk about some future directions, etc. So hopefully it'll be exciting. I mean, virtual memory is an exciting topic by itself. As I mentioned in the last lecture, this is a concept that has been around since the 1960s, and it really needs a serious rethinking, as we will see in some of the issues, and as I will recommend you to potentially study if you're interested in this. But it is pervasive, it's everywhere. It's one of the very successful ideas, but I still believe that we need to really think critically about virtual memory today so that we can scale it much better, or at least scale the advantages it provides to us much better in a different way, potentially, for our future systems. Okay, so let's jump in. I'm going to go through this relatively quickly. You know that you have some readings that would help. And recall in the last lecture, we introduced the downsides of direct physical addressing from load and store instructions. And I'm not going to discuss that again, but virtual memory gets rid of a lot of those downsides of direct physical addressing, which leads to basically direct physical addressing has issues with relocation, isolation, protection, as well as programmer being involved in managing memory. But the idea of virtual memory is to give each program the illusion of a large address space while having a small physical memory, so that programmer doesn't worry about many things, managing the physical memory, managing different processes, and programmer basically safely assumes that they have an infinite amount of physical memory and they're happy, hopefully. As we discussed, hardware and software cooperatively enable this. And we started looking into the hardware and software support for virtual memory, and the illusion is maintained for each independent process. And this was one of the pictures that I used to give you the idea. Basically, you have multiple different virtual address spaces belonging to different processes. It could be within the process also, potentially, but we didn't talk about that, and we're not going to talk about that really in this lecture. And you map it to physical address space that is of limited size or much smaller size. And this requires indirection and mapping, as we discussed. And we introduced the idea of a page table, which does both the indirection as well as the mapping by doing address translation from virtual addresses generated by CPU's load and store instructions to physical addresses that are required to access physical memory. And you can see that page table is the mechanism that enables address translation. It's a lookup table, essentially. It's OS-managed lookup table, but hardware has access to it through the memory accesses, and hardware caches it, as we will see. And page table tells you whether the virtual page you are accessing is in physical memory or not. And if not, it helps you, at least the system, the virtual memory system helps bring the page from the disk into the physical memory. As a result, physical memory is a cache for the disk, and we've studied caches for the past few lectures, so you know how a cache is managed, and we're going to look at that a little bit more within the context of physical memory today as well. Okay, and recall we were discussing 4 issues in indirection and mapping. We discussed actually a bunch of these. When to map a virtual address to a physical address. Usually it's demand-based, but you could do prefetching, which is another idea which we had discussed as well. What is the mapping granularity? We're going to talk a little bit more about that today. It's essentially page size today, but then the question becomes, what is your page size? Is it 4 kilobytes, 16 kilobytes, 64 kilobytes, 1 megabyte? Do you want multiple granularities? In existing systems, there are multiple granularities as well, because there are clear trade-offs. If you have a very small page size, then you may not be, you need very large page tables, and you may not get very good locality also when you bring things into the physical memory. If you have a very large page size, your page table size becomes smaller, clearly, because you need to store fewer pages in the page table. And you may get very good locality when you transfer a large page into your physical memory if you have very good spatial locality. But if you don't have very good spatial locality, you may be transferring a 1 gigabyte page into your physical memory and using only 8 bytes of it. As a result, it doesn't work very well. So there are clear trade-offs between large pages and small pages and different granularity pages, just like we discussed with large blocks and small blocks in caches. That's why physical memory looks very much like a cache to disk. And it is actually when we talk about virtual memory. We talked about where and how to store the virtual to physical mappings. That's page table essentially, but we're going to cache it in the hardware today. What to do when the physical address space is full? Essentially, we need to evict some page that we cached in the physical memory. And how do you decide that? It becomes problematic because we're dealing with a very huge physical memory address space, especially today, right? So we're going to talk about some of these issues in a bit more detail today. But recall this another slide that we used physical memory as a cache. It's a cache for pages stored in disk. So as a result, similar, all types of caching issues that we discussed in the caching lectures exist here as well, plus prefetching. Basically, any kind of management mechanism, placement, replacement, granularity of management, write policy, instructions versus data, all of those actually arise here as well. Okay, some definitions just to get you on the same page again. No pun intended with the page over here, but essentially page size is the mapping granularity, as we discussed. It also dictates the amount of data transferred from hard disk to DRAM at once. You could optimize that. You could sub-page things, just like we did sub-blocking, if you remember, in caches, right? But you need to be very careful about this because now things are exposed to software, which is the operating system. Page table, I've already said that multiple times. It's a lookup table that's used to translate virtual page addresses to physical frame addresses. And address translation is that process, essentially, that translation process. And this was one picture that I showed you. Ideally, you would get most of the CPU accesses hit in physical memory, but some accesses miss in physical memory. So you will need to bring the data from the hard disk. And hopefully you get the best of both worlds, the latency of physical memory and the large capacity of the hard drive. Okay, and this is a picture of address translation. I'm going to show you a more generic picture later, but this is the example that we were doing when we finished the lecture. We finished the lecture with finishing with these examples, if you remember. And you can follow this example from the last lecture or your book as well. Book actually has this example. And this was the example. I'm not going to go over it again, but clearly this shows you how to do the address translation. You index the page table with the virtual page number. How do you find out the virtual page number? You make sure you chop off the page offset, just like you do in a cache access, where you chop off the byte and block. And then a page table, now you can also calculate the size of the page table. It needs to have 2 to the 19 entries, as you can see over here, because you have 19-bit virtual page numbers. And in this case, you index it. Basically, the processor needs to do a memory access to a page table entry located at offset 2 from the page table base register, which is in physical memory, essentially, which is a pointer to the page table in physical memory, essentially. And in this case, it happens to be that location says the page table entry is valid, which means that the physical page corresponding to the virtual page you're accessing is in physical memory, and this is its physical frame address. And you basically take that and concatenate it with the page offset. That leads to the physical address that we're accessing. And remember, page offset bits do not change during translation. And hopefully you remember all of this. Okay, recall that we were discussing the issue of page table size. This is where we almost left off, actually. We wanted to calculate the size of a page table, and I increased the size similar to today's sizes today. A virtual address today could be easily 64 bits, and that's a huge address. And if your page is 4 kilobytes, then your virtual page number is 52 bits. Basically, if your physical address is 40 bits, that's 2 to the 40, which is a reasonable, respectable physical memory size today. Then your page table needs to do a translation from 52-bit virtual page numbers to 28-bit physical frame numbers, which means that it needs to have 2 to the 52 entries. And assuming each page table entry is 4 bytes, this is 2 to the 54 bytes. Now, this is larger than your physical memory, right? And your page table needs to be stored in physical memory. So we have a problem here. We need to access physical memory. We have to go through the page table. To be able to do the translation through the page table needs to be stored in memory, but we do not in physical memory, but we do not have enough physical memory to store the page table. So clearly this is not going to work, right? And this is just for one process. As I said, each process has its own page table, and the process may not be using the entire virtual memory space. So even though it has a 2 to the 64-bit access to 2 to the 64 addresses, it may be using a very small fraction of it. But the way we describe the page table, you still need to store every translation for every virtual page number. So this is essentially doesn't work in existing systems. Basically, the page table is large, and at least part of it needs to be located in physical memory. You can say, okay, maybe I can locate, I can put parts of the page table in virtual memory also. But you need to be careful about that, because you should be able to translate the page table as well, right? But at least part of it needs to be located in physical memory so that you can actually find out where the other parts of the page table are in virtual memory and then bring them from the disk. Okay, so it's large, and if it cannot be fully accommodated inside the physical memory, so what do? Basically, people have developed the idea of multi-level or hierarchical page tables, where you have you organize the page table in a hierarchical manner such that only a small first-level page table has to be in physical memory, and all of the other page tables can be in virtual memory. And you need to you go through the translation process to bring the page table into the physical memory before you can actually do the translation of the address that the processor generates, right? Now it's multi-level translation, as you can see, and it's fun to think about, but this is the idea of multi-level or hierarchical page tables. And this is again from your book. Basically, it looks like this. Instead of dividing the virtual page number into a single monolithic piece and indexing a single monolithic page table with that, we divide the virtual page number into two pieces, which lead to a two-level hierarchy. The topmost 9 bits, in this case, provide us the page table number. And this is the first level page table, essentially. This has to be in physical memory. And then after we get the translation of that address, of that part of the address, this provides a pointer to the page table base registers of other page tables. So if you look at the first level page table, it's 2 to the 9, 512 entries. And each of them points to a page table that contains 2 to the 10 or 1K entries. Essentially, this is a hierarchy of page tables you have right now. The real page table is actually here, second level page table. But to be able to access their second level page table, you need to go through another level of, let's say, indirection, or another level in the indirection, so that you can actually get the page table entry you're looking for that corresponds to the full virtual page number. So basic idea is very simple, as you can see. Instead of having a single virtual page number indexing a monolithic page table, chop the virtual page number into multiple pieces, and first index a small page table that has to be in physical memory, and then using the base register that is provided by the page table over here, index another page table to really get the translation that you're looking for. So this is fun, as you can see. And as I said, only the first level page table has to be in physical memory, which can be very accommodatable, as you can see over here now. It's only 2 to the 9, 512 entries. And if each entry is 4 bytes, then it's only 2 kilobytes, right? Very small. Okay. And only the needed second level page tables can be kept in physical memory. For example, if the process is not using the entire address space over here, this is a 32-bit address, by the way, it's from your book. It may be actually a 31-bit address, I don't remember. It's a 31-bit address, actually. It's the same example that we're following. Basically, if any of the other parts of the virtual memory is not used by the process, you don't even need to have a page table for that, basically. If some part of the virtual memory is not allocated by the process, you don't need to have page tables for it. This way, you can really compact the storage of the page table significantly. And this is just 2 levels. You can also extend the idea to multiple levels. But what is the downside? The downside is now each translation requires additional latency, right? You can see that you first need to translate this page table number to get the page table base register. And then you need to do the real translation by getting the real physical page number corresponding to the entire 19 bits over here. So it's a 2-level access. So you need to do 2 memory accesses to get the translation, and then 1 memory access to actually do the memory access you're supposed to do, right? So clearly this increases the latency. So another level of indirection always increases latency. So we added 1 level of indirection, monolithic page table. Now we're adding another level of indirection, 2-level page table. You can add another level by making it a 3-level. Clearly, that way you can reduce the storage that you have to have in physical memory for a given process. And also you can basically ensure that a large amount of the page tables are not allocated if the process is not using the entire virtual memory, or if it's using a small fraction of the memory. But the trade-off is between the latency and this capacity, memory capacity trade-off. And this is a very fundamental trade-off. Latency and capacity always go against each other, as we have seen between in caches, right? You want to build some big memory, but big memories are slow. And this is very similar in a sense. We're making it smaller so that we can make it faster. Yeah. Okay, basically, this is an example of the translation. I'm not going to go through this in detail, but this is our 31-bit address. How do you actually get the translation for it? You basically take the top 9 bits and access the page table, the first level page table, which gives us the page table base register for the second level page table. In this case, it's valid. So it's the second level page table that we're looking for is inside physical memory. So we can take that address, add to it the page table offset to get the translation that we're really looking for. And that's our physical page number. We concatenate it with the page offset. Now, if this translation was not valid, meaning the page table base we're looking for was not in physical memory, then we need to actually bring the page table that we're looking for into the physical memory first, which is also handled by the virtual memory system. So virtual memory system manages the page tables, not only the translation, but also bringing in the page tables from memory as well. Okay, so as I said, for an n-level page table, we need n page table accesses to find the PTE. So latency increases, and a page table access is a memory access, essentially, right? As we have discussed in the last lecture. So this is a real example from an x86 architecture. This is a 2-level translation, as you can see, as we have seen earlier. Basically, your linear address is divided into 3 pieces. Offset is the page offset. For 4 kilobyte pages, it's 12 bits, as we discussed. And they basically divide into page directory. They call this part page directory. It's a directory of page tables, essentially. And the second level page table is accessed based on the page directory entry plus the offset from the address over here, coming here from the table. And you can see that in x86, CR3 is the control register 3 that points to the physical page table base register they call it actually page directory base register over here. And this is a part of the process. So whenever you context switch in a process, the CR3 needs to be put into the processor. So it's part of your hardware context, as we also discussed in the last lecture. Basically, CR3 is a special name in x86 architecture uses for the PTBR, page table base register, as we know it from our lectures. But as you can see, this is real. It's going to get a little bit more complicated. So in this case, it's page directory base register because it's multi-level, as we said, right? Okay, does the file system map paths to virtual memory? And the answer is actually yes. File system, whenever you load a file, you also do it, map it into physical memory, and you go through the virtual memory to access the file. And we will see an example of this later on, but not in great detail. You will see more examples of this in systems programming course when you will see. But modern file, and you can also read the unassigned parts of your book, which talks about memory mapped IO, for example, memory mapped files. So files whenever you access a file, they get memory mapped through the virtual memory system, and you do loads and stores into the file later on. So very good question. We will see how that is exploited in RowHammer in a little bit, but not yet. Okay, so this is for small pages. This is exactly the same picture, actually, shown in a different way. You can see that this is the virtual address. x86 calls it linear address. This is for 32-bit addresses. x86 now has 64-bit addresses, as we will see later on also. But you can see how they do it, basically. Page directory is very small. It's 2 to the 10 entries. And CR3 gets concatenated with the directory entry over here so that you can access the physical address over here. And then you get the address of the page table you're looking for. You find your PTE from an offset coming from these bits. And then you basically form your physical address, as we have discussed. Right? So it's basically, as we have discussed, it's multi-level. This is a large page in x86. It's a 4 megabyte page. It also has multiple pages, as I said. Whenever you allocate a page, you can decide what size of a page you use, actually. And you can see that this 4 megabytes, it doesn't require a 2-level address translation, because if your pages are large, your page directory is small to begin with, basically. So you just go through what they call a page directory. What I think they should have called a page table, but to be consistent with what is shown over here, they call it the directory. But this is really the direct page table for 4 megabyte pages, as you can see. Right? And it's a very small page table because your pages are very large. Okay, and this is the x86 64 addressing. this is actually there are 64-bit addresses, but the top 16 bits are not used because there are no, at least people have not perhaps found use for 2 to the 64 byte virtual memory. So the largest virtual memory you can get is 2 to the 48 bytes, which is 256 terabytes. But of course, I'm thinking in the future they will need to extend it also. But they're dealing with 48-bit addresses, and you can see that now there are 4 levels. This is the first level, 9 bits, and this has to be in physical memory. And then you index into another level. Say they call PML4. I don't remember what it stands for, but PLM4 extended over here actually. And then page directory pointer extended. That's what E means over here, or maybe entry actually. These are entries, sorry. And then page directory entry, and then page table entry. So this is, you do a 4-level page table lookup just to get to the page table entry that you're really looking for. And then you do the translation over here. Okay, so clearly this is a lot of accesses, and this is real. This is what happens in your x86 processors if you're using x86. Okay, but we solved the problem basically. Page table is large. We made it multi-level so that only a small fraction, very small fractions, has to be in physical memory. So we don't waste physical memory address space. This hierarchical page table also enables us with the ability to not allocate page tables in virtual memory. So we save the allocation of page tables if the process is not using a lot of virtual memory space, basically. Okay, exactly how it's done, that's beyond the subject of this course. So you can read more or take the systems programming, and I don't know how much detail systems programming goes into in terms of virtual memory subsystem and how it interacts with the file subsystem as well. Okay, so the second challenge, of course, which is exacerbated by the first solution for the first challenge, is each instruction fetch or load store requires at least 2 memory accesses now. One for address translation, you need to reach the page table. I should say at least one for address translation, because with a multi-level page table, you need more. And then one to access the data with the physical address after translation. So you used to have 1 memory address with direct physical addressing. Now we have 2 at least. So you need to have 2 memory access to service an instruction fetch or load store, and that greatly degrades execution time. Each memory access takes, I don't know, if it misses in the caches and it takes 100 nanoseconds, then you're in trouble. And you're in bigger trouble if you have a multi-level page table, because the number of memory accesses increases with the number of levels in a multi-level page table. Unless you're, of course, clever, right? Unless you have a mechanism to speed up the translation, and we're going to be clever. We're not going to tolerate, we're not going to basically tolerate this latency overhead of indirection that is very costly, and we're going to speed it up. And to speed it up, we're going to use an old trick in our bags, right? And that's the idea of caching again. So these translations, they could have very good locality, because whenever we access a particular location in virtual memory, it's likely that we're going to access location again, or locations around it again. So we can get both good temporal locality and spatial locality just because of the way things are done, just because of the way programs are written, as we discussed in caching, right? So the same locality applies here as well to the translations. So why not cache the page table entries in a hardware structure in the processor to speed up the address translation? That's the idea of a translation look-aside buffer. It's essentially a cache for page table entries that you can access within one cycle or just a few cycles, such that you can get your addresses translated right away without going through the page table. And this is called the translation look-aside buffer. Again, we're not caching the data, we're caching the translations. But since we're going to access the data, if the data has locality, translations should have locality as well, right? Because these are coupled with each other. And we have seen that data has locality, physical, spatial, and temporal locality. It's going to be no different in this case. So it's really a small cache of recently used translations, or PTEs, page table entries. In fact, in each TLB entry, you have a page table entry. And the idea is to reduce the number of memory accesses required for most instruction fetches and loads and stores to only 1. Well, not even 1 actually, because the translation look-aside buffer cannot be considered memory. It's really a cache. So basically, you reduce it to a cache access. You get the translation right away without even accessing memory. But of course, for the first time, you need to bring the translation to the memory, into the cache, and store it there, into the translation look-aside buffer, and store it there. Okay, So why does this work? As I said, page table accesses have a lot of temporal locality just because data accesses have a lot of temporal locality as well as spatial locality. It should be temporal and spatial locality over here. Actually, I should edit it over here. Okay, that sounds good, hopefully. And we can discuss that later on also. But large page sizes aid spatial locality actually a lot. If you have a gigabyte page size and if you're actually traversing a gigabyte array and your translation granularity is gigabytes, then you just need one single entry, right, in your TLB as well as the page table. And consecutive instructions and loads and stores are likely to access the same page, as we have discussed many times. So TLB works just because other caches work, and TLB is a cache of page table entries. And it's small, usually accessed in the order of 1 cycle or 3 cycles, somewhere around that. Typically, its size is small at level 1. It's actually 512 entries is quite large for level 1. And typically, just like any other cache hierarchy, you can have a TLB hierarchy as well. Later on, we will see an example of this. Usually, it's highly associative. Usually, you get very good hit rates, but depends on the workload. If you're doing random accesses, of course, then you have a problem, right? Or if you're randomly going through memory, then you don't have locality anyway, and TLBs exploit locality. It reduces the number of memory access for most instruction fetches and loads and stores to only 1. And if you hit in the TLB, actually, you don't need to access memory. And this is an example 2-entry TLB from your book. Basically, it's like a cache. This is a 2-entry cache, 2-way associative, meaning fully associative. And you can see that it's very simple. What do you do? Basically, you index it using the virtual page number. And essentially, in this case, it's also tagged. There's no index because it's fully associative. The virtual page number is your tag also in the entry. And each entry the stores the data of each entry is the physical page number. Actually, it's really the PTE, page table entry over here that's stored. But for simplicity purposes, this shows only the physical page number. But basically, you search the TLB using the virtual page number. And if you find a valid translation, valid PTE corresponding to that virtual page number cached in the TLB, you can do the address translation very quickly. And that's what we show over here. So hopefully this is a simple idea after you know about caches, right? And as I said, TLB is a translation or PTE cache. It caches PTEs, page table entries. And all issues we discussed in caching and prefetching lectures apply to TLBs. For example, usually TLBs are split between instruction and data because they're needed in different parts of the pipeline. And we discussed the advantages and disadvantages of instruction and data. Caches, same things apply to TLBs. We have multi-level TLBs, we have associativity, choices in terms of size, trade-offs in terms of block size, etc. All of them apply. Insertion, promotion, replacement policies. Again, you want to keep in the TLB most useful translations that are going to be needed in the future. And all of that apply. What to keep in which TLB and how to decide that, prefetching into the TLBs. Keeping TLBs coherent. We talked about cache coherence a little bit. That also applies. Shared versus private TLBs across different cores and threads, that also applies. So everything related to caching that we discussed applies to TLBs because they're also caches, except they cache translations, they don't cache data. Okay, so let's go into a little bit more detail into virtual memory support and examples. I'm going to go through some of these quickly because some of them are actually redundant slides that, based on what we have discussed. But feel free to ask questions. So as we discussed, virtual memory requires both hardware and software support. If you do it in just software, if you don't have TLBs, your performance is terrible. So it's a bad idea if you don't have hardware support. You should really have hardware support for virtual memory. And at the very basics, you need to have support for translation, meaning accessing the page table. But TLBs is a no-brainer if you have virtual memory, right? So page tables in memory, it can be cached in special hardware structures called TLBs, as we discussed, right? So the hardware components of the virtual memory is usually called the MMU, or memory management unit. And this is usually a per core unit. Every core has a TLB, for example, L1 TLB and L1 data TLB and instruction TLB. But also it includes other things. It includes page table base registers, TLBs, page walkers. We will discuss that. So some systems do the page walk automatically, meaning in hardware. In hardware, you may actually do the multi-level page table walk, and you may use specialized hardware for that. And we will discuss that from a real example from Intel systems at the end of this first lecture. So it is the job of the software to leverage the MMU to populate the page tables, decide what to replace in physical memory, but it could also be the job of the hardware in contract with the software. And the software definitely has to change the page table base register on a context switch so that you can use the running threads page table. And software needs to handle page faults and ensure correct mapping, as we will see in a little bit. So address translation, we've already discussed this. Basically, page size specified by the ISA. Old times, the page sizes were smaller. Now page sizes are bigger, and there's a push for having multiple page sizes, small and large pages. Clearly, there are trade-offs here. I've discussed that in multiple lectures, so I'm not going to discuss it right now. And we've already said that, defined all of these terms. So let's take a look at what's in a PT, what's in a page table entry, because it's going to be interesting. We saw some things, but let's take a look at it more. So a page table is a tag store for the physical memory data store. It's a mapping table between virtual memory and physical memory. And page table entry can be thought of as a tag store entry for a virtual page in memory. So you need a val bit. You need to indicate validity of or presence of this virtual page in physical memory. You need tag bits, physical frame number or physical page number to support translation, of course. You need bits to support replacement. What page gets replaced from physical memory if the physical memory is full and you need to bring in another page from the disk. You need to have a dirty bit to support write-back caching, because in physical memory, when you write to a physical memory location and that location, that page needs to get evicted, what do you do with that updated data? Usually we have a write-back physical memory, meaning you don't expose all of the writes that you do to physical memory to the disk, right? That is unreasonable because it's too slow. So you need to have support for writing back. You need protection bits to enable access control and protection. And this is going to be important in our later discussion because virtual memory provides support for memory protection as well, not just address translation. So this is my cartoonish picture that basically shows all of these. And I'm not going to go through this cartoonish picture, but we're going to examine it. But I guess one thing that is shown over here is the R bit, reference bit, access bit. Was the page referenced recently? This is one way of doing replacement or helping replacement. You basically have a single reference bit or access bit, also called in some operating systems. You basically say whether this page was recently referenced. And if the R bit is set or A bit is set, access bit in x86, it's called an A bit actually. Basically, if the R bit or reference bit is set, this means that the page has been referenced recently. So don't evict it or try not to evict it from physical memory. That's the idea basically. So a single bit can help you replace things in a nicer way. And you have actually a lot of time in replacement, in page replacement. Okay, address translation we've seen before. I'm not going to go through this again, but this is a generic address translation picture. You can study it on your own. And we already discussed the page table structure. Again, this is generic. We discussed a hard-coded page table structure, but this is more generic with NMP, as you can see over here. And we already discussed address translation and page table entry, what it provides. I'm not going to talk about that. But let's take a look at what the MMU does when you get a page hit, meaning address translation hit. So, I mean, these are actually obvious steps. So I'm going to go through this quickly, but we're going to build up to the page faults in a little bit. So this is the easy case. Processor sends a virtual address to the MMU, including the TLBs. MMU fetches the PTE from page table in memory or provides it from the TLB. And if you get a hit, you basically MMU sends the physical address to the L1 cache, and L1 cache sends the data word to the processor. This is assuming that L1 cache is physically addressed. We will take a look at that later on in this lecture without going into a lot of detail. Okay, so this is an easy case. What if you have a page fault, meaning the page that you're trying to access is not in memory? So again, it starts with MMU fetching the PTE from the page table in memory. It finds out that the val bit is 0. So MMU triggers a page fault exception that software needs to handle. It could also be handled by the hardware, but software usually handles page faults in modern systems. Handler now identifies the victim page meaning which page. So basically, you need to bring another page from the disk to memory, assuming that the physical memory is full. If the physical memory is not full, then you basically bring a page from the disk into an invalid frame in physical memory, obviously, just like in caches, right? If it's full, the page fault handler identifies a victim page, and it basically replaces it with the new page coming from the disk. Of course, if the victim page is dirty, it needs to be written back to the disk, right? And then the page fault handler pages in the new page and updates the PTE in memory. It changes the translation, basically. And it changes the translation for the evicted physical frame as well. So think about how to do that. This becomes difficult. How do you figure out the evicted? How do you figure out the page table entry for an evicted physical frame? Page table provides mappings from virtual to physical. But now you're trying to invalidate a mapping using the physical frame number, physical address. How do you index the page table? You cannot, because page tables index using the virtual page number, right? So a lot of operating systems actually sometimes use some inverted page tables also or some hashing mechanism to actually figure out the backward mapping from physical frame to virtual page as well. So there are a lot of details over here that are actually that make the system extremely complicated, and that's one of the reasons why virtual memory is amazing, in the sense that it's been extremely successful, even though it has added a lot of complexity into the system. So supporting virtual memory in the old system actually was not easy because it was very costly. Okay, and then the handler returns to the original process, restarting the faulting instruction, because now you have the data that you need inside physical memory, so you can restart the access and access the physical memory. Okay, so page fault handling actually is a lot more, and I'm going to give you an overview without going into a whole lot of detail, but I've given you one example complexity that is introduced when you evict something from physical memory, right? Okay, I mean, we've discussed this already. You incur a page fault exception when you access a page table entry that doesn't have the valid bit set, and you invoke an OS interrupt or trapped handler, exception handler actually. Other processes can continue executing, but this process needs to stop. And OS has full control over the placement. So before fault, you actually access something on the disk, and that needs to be brought into the physical memory, as you can see over here. So basically, in this case, the mappings of other stuff remains unchanged, but you actually have another mapping that's introduced. Now, one page is not in disk anymore, it's in physical memory. Okay, so let's take a look at it a little bit more detail from the system perspective. So processor, to service the page fault, processor needs to signal the IO controller so that the IO controller reads a block length of P, page size, starting at some disk address, and store starting at memory address Y. So basically, you need to do a disk to memory transfer. And this needs to be orchestrated by the operating system, which also needs to know exactly where in disk the page you're looking for is. So there's another data structure that has that information. It could potentially be stored in your page table, assuming it fits into your page table, but we're not going to go into that. Assume that it's a separate data structure for now. So disk to memory read occurs after that through some direct memory access transfer without hopefully disturbing the processor. It happens under the control of this IO controller over here. And then when the controller finishes the transfer, it interrupts the processor, saying that I have finished the page fault request that you asked me to service, and the operating system resumes the suspended process after, of course, fixing the page table entries, etc. Right? Okay, so there's a lot that goes on to service a page fault, and that's what you need to know for this course. Okay, so page table replacement algorithms, clearly this is similar to page replacement algorithms, but a little bit different in the sense that physical memory is huge. So if physical memory is full, meaning list of free physical pages is empty, which you need to also keep somewhere, if you think about it. So there's a lot more complexity I'm adding right now, but you can think about how to do that. Which physical frame should you replace on a page fault? Okay, so is true LRU feasible? We have 4 GB memory, 4 KB pages. How many possibilities of ordering? So true LRU is not even feasible in a 32-way associative cache. Now it's actually huge, right? So it doesn't make sense. And true LRU is not necessarily a good idea anyway, right? Because as we discussed, access patterns are not always LRU friendly. So modern systems usually use approximations of LRU, just like we do in caching, except in physical memory, we have a huge physical memory. So this is really a rough approximation of LRU. So the clock algorithm is one example we will discuss briefly. And there are more sophisticated algorithms that can take frequency of use into account. Actually, you can afford some of these more sophisticated algorithms because it takes long to service a page fault, right? You need to do a disk access. And while you're doing the page fault handling of the page that you need, you may decide, okay, I'm going to take some time to pick which page in my physical memory to replace, because you have a lot of time. So you can actually afford some sophisticated algorithms over here. And that's the difference from caches here. So the ARC algorithm is actually one of the famous ones. I would recommend you take a look at it if you're interested. It takes into account the frequency of use. It's developed by IBM, and it's used in some of their operating systems. Actually, newer versions of it is used in some of their operating systems. And you can take a look at this paper if you're interested. Okay, let's talk about the clock page replacement algorithm. This is a very simple page replacement algorithm that was used in early systems, early Linux, for example. Now it's more sophisticated. But basically, it looks like this. For each page in physical memory, you have a reference bit. And basically, you have the hand of a clock. And you start going clockwise, trying to find a page whose reference bit is set to 0. And once you find a page whose reference bit is set to 0, you say, okay, this is my victim. I'm going to replace that. You basically skip through all pages whose reference bits are 1. And that's the idea, basically. And these bits are periodically cleared. They're set when you access the page, when you need the translation, basically, when you need the page. They're cleared periodically by the operating system. So this turns out to be a relatively cheap algorithm to implement in terms of both cost, both storage overhead and latency. And usually you find something to replace. And usually it works reasonably well, basically. So I've given you the idea, but let's go through it relatively quickly also. I keep a circular list of physical frames in memory. Operating system does. So the operating system does all of this, basically. Keep a pointer or hand to the last examined frame in the list. When a page is accessed, you set the reference bit in the PTE. Remember, I showed you those. When a frame needs to be replace the first frame that has the reference bit not set, 0, traversing the circular list starting from the pointer hand clockwise. Okay, very simple algorithm. During traversal, one option could be to clear the R bits of examined frames. In this particular case, that's what I wrote here, but you can also periodically clear it. You can do it during traversal, which reduces the overhead of periodic clearing. Basically, there are different methods for clearing it. And then you set the hand pointer to the next frame in the list. Okay, so this is very simple. This tries to figure out which one has not been referenced recently, right? Which page has not been referenced recently. Okay, so a cache versus page replacement. Physical memory is a cache for disk, as we discussed. It's managed by the system software via the virtual memory subsystem. Page replacement, as a result, is similar to cache replacement. You can actually imagine implementing clock type algorithms in a set associative cache also, and it works not so badly. Page table is the tag store for physical memory data store, as we discussed. So the difference is the required speed of access to cache versus physical memory. Cache needs to be fast usually. Physical memory is slow. In fact, whenever you get an eviction, it's even slower. So you have more freedom in your algorithms and page replacement. Number of blocks in a cache is smaller than number of blocks in physical memory. So you have some more overhead, tag overhead in physical memory. So you cannot really afford extremely sophisticated algorithms that require a lot of storage. And the tolerable amount of time to find a replacement candidate is different. Disk latency is much higher than memory access latency. So the caches are at a disadvantage here, whereas physical memory is at an advantage. And the role of hardware versus software. So in general, in our discussions of hardware caches, we said they're hardware managed, right? We don't usually manage the caches through software. The replacement is done, placement is done, insertion is done, promotion is done. All of it is done by the hardware. But in physical memory, software has a role in management, and replacement is one of the big roles in software. Setting the access bits is the job of the hardware, usually the reference bits, but the replacement itself is the job of the software. So virtual memory is a nice concept where responsibilities are divided in a nice manner between the hardware and the software, but complexity is not avoided. Basically, complexity is still there. Okay, so now let's talk about memory protection, which is another thing that virtual memory provides. Basically, as we discussed, I don't see any questions, so I will keep going essentially. So virtual memory provides address translation and indirection mapping, which is a lot of benefits. And one of the benefits that this enables, especially page-based virtual memory, is memory protection. As we discussed, multiple programs run concurrently. Each process has its own page table. Each process can use its entire virtual address space without worrying about where other programs are. And a process can only access physical pages mapped in its page table. It cannot overwrite memory of another process. So this provides protection isolation between processes. That's the beauty of page table-based isolation. And it enables access control mechanisms on a per page basis. So it can actually set these protection bits and isolation guarantees on a per page basis, on a page granularity. And you can do sharing and access control on a per page granularity. Right? So let's take a look at this over here. So each process has its own virtual address space. Each process sees the full address space. And this simplifies many things as we have discussed in the past. I'm not going to discuss it again. But each process can have access to its own pages, but they can also share the pages, as you can see over here. So different processes, different virtual addresses can be mapped to the same physical page. This could be read-only library code, right? You don't want to necessarily replicate it. It could be some shared data between the processes that can be allocated using system calls also. But for example, you can say that this virtual page that I'm accessing cannot be accessed by anyone by setting the page table entry access to the level that you want for this process. And we will see examples of this. So there's one question. Is there also something like prefetching for optimizing page accesses? Yeah, absolutely. Just like caches, you can prefetch translations into the memory hierarchy as well. Okay, so page level access control. So not every process is allowed to access every page, and that is supported by virtual memory. So you need supervisor, or modern name is kernel, level privilege to access system pages, for example. Right? You may not be able to execute instructions on some pages. People actually more recently in the grand scheme of things, non-executable pages were introduced so that you cannot just write some data to some location and jump to it and then execute some malicious code, for example. So the idea is to store access control information on a page basis in the process's page table. And I've already said this. And during hardware translation, you enforce access control at the same time. So concurrently with translation, you check whether you have access to this page. So virtual memory system, as a result, serves two functions today. They're independent of each other. Address translation provides the illusion of large physical memory, plus other benefits, as we discussed. Access control, protection, essentially protects different processes. And even within the same process, you protect different pages so that you don't do something malicious to some pages that are important potentially. And this is my cartoonish picture, basically, that shows exactly the same thing if you're interested. Translation and access control. So if anybody asks you the two things that virtual memory provides, two functions virtual memory provides today, that's it, translation and access control. Okay, so this is an example. Again, we extend the page table entries with permission bits. And permission bits can say whether you're allowed to read the page, write the page, execute the page. So you can imagine different things over here. And then you check the bits on each access during a page fault, or even a TLB access, right? It doesn't have to be during a page fault. But if violated, you generate an exception. And this is called an access protection exception. And when you get an access protection exception, the operating system gets involved. And it basically usually kicks you out of the system or stops the process, basically, because the process is not supposed to access that location because it happened for some reason, right? Okay, so that's how you enforce. Basically, during the translation, while you're doing the translation, in the TLBs, you enforce this also. Okay, let's take a look at these protection levels in x86. x86 doesn't necessarily have the best protection architecture, but I'll show example from x86. Basically, you have different levels of protection called protection rings. Kernels at level 0, applications are usually at level 3. And if I have to actually look at these, usually you make use of ring 0 and ring 3. Supervisor is the same thing and kernel in modern terminology, and the rest is users, if you will. And if you look at the page directory entry and PTE of an x86 manual, it basically shows you something like this. So it's like a page table entry. So you can see that PDE for 4 megabyte page, PDE for the page table, not present PDE. So they show you different things, basically. If not present, you ignore the rest of the things. But let's take a look at this. This is the PDE. You can see that this is the valid bit. This is whether you can read or write to it. This is whether you need to have user level or supervisor level access to it. And an access bit, this is the same as reference bit. And then address of the page table. Same thing happens for page table entry. This is the second level page table entry. This is address of the 4 kilobyte page frame, as you can see, and the same protection bits also exist over here, but the format is different because this is the second level. Okay, just to show you that basically. And then there's, of course, description in the instruction set architecture that says what these bits mean, okay? And this is the PDE. PDE protects all 1024 pages in a page table. This is the first level page table. And then PTE protects one page at a time. So you have multiple levels of protection also when you have multiple level page tables. So that's another benefit of multi-level page tables. You can get multiple granularity protection to some limited extent. And you can see, I'm not going to go through all of this clearly. You can see, if you're interested, these things. And then there are fun combinations of it, basically. The protection is a function of PDE plus PT in the end. And then you have some combined effect that is also described in the manual. And yeah, now you're starting to see how complicated things can get, right? When you have multi-level page tables, plus access control, and plus different types of access control. And I'm not going to go through this in detail, but you can read it. But let's talk about something that ties the lecture we're having to something we talked about at the beginning of the class, which is RowHammer, right? And hopefully I'm going to give you an understanding of how RowHammer violates the virtual memory protection mechanism that we just saw, basically. Basically, virtual memory protection says, you just, if you're a user, you cannot access a supervisor level page. If your access type is writes, and if you're reading a read-only, if you're trying to write to a read-only page, you should not be able to do that, right? And that works, right? That should work, basically. But unless someone can flip your bits, unless your hardware is unreliable and someone can flip the access protection bits, right? Such that a user-level program can gain supervisor-level access. And that's what happens with RowHammer, for example. You can, for example, flip the access control bit from user to supervisor, if you're lucky, or if you're careful. Can this happen? Well, you know the answer, basically. It can happen in RowHammer. I'm going to give you an example of how it happens, but I'm going to remind you what RowHammer is also very quickly, because we have studied it. Maybe you didn't appreciate what that is at the beginning of the class, but maybe you will appreciate it right now, because now you know actually how virtual memory protects memory pages and how you can circumvent that memory protection. I'm going to actually show you how Google did it in their first attack in 2015 based on our work. Okay, we know that you can predictably induce bit flips in DRAM chips, and this leads to a system security vulnerability. The question is, why does it lead to a system security vulnerability? Let's remember what this is. Basically, if you keep activating and pre-charging, meaning applying high voltage and low voltage, to a single row in DRAM, you can get bit flips in adjacent rows. That's the idea. Clearly, this is not supposed to happen because you're changing these victim rows, and the victim rows may belong to different processes, different page table entries. Now it may make sense. And we're going to see how you can actually flip bits in important page table entries so that you can gain access to the entire system. Okay, so you can actually do this hammering in a real program that looks like this. A real program, actually, which is interesting. Now you know probably a lot of this. Maybe you don't know what cache line flush is, but this basically flushes the cache line from the caches. So what this program does is it selects address X and Y such that they map to the same bank. It avoids cache hits, because you need to avoid caches so that you can access memory and flip the bits in memory. You need to avoid the row hits. You need to avoid the row buffer as well. And you know all of these structures by now. You need to avoid all kinds of caching in the system so that you access rows X and Y in the system. And this simple program does it, actually. You need to select address X and Y carefully, of course. Okay? Actually, you can eliminate the mfence, ignore what that is for now, but Google in their program eliminated it later on. This is our original program from 2014. Okay. And we showed that you can actually do this in real systems and you can get a lot of bit flips. Now, we said that you can take over an otherwise secure system. Somebody can hijack your computer by taking advantage of those bit flips. And Google folks actually showed that, if you remember, in an earlier lecture, we discussed it. And I actually showed you the slide where I copied and pasted from Google's blog post, where they basically said they replicated the problem based on the information provided in our paper, in ISCA 2014 paper over here. And they built two kinds of attacks. One of them was very interesting, as I said. As an unprivileged user-level process, you basically can escalate privilege. You can gain kernel privileges on x86 for Linux. And they basically, as I said, if you don't, maybe you don't appreciate it at the time, but right now you can appreciate it. On a machine vulnerable to the RowHammer problem, the user-level process induces bit flips in page table entries, and it can gain write access to its own page table. And once you gain write access to your own page table, what can you do? You can set your permission bits, right? Because you know the page table structure, it's public. And then gain read-write access to all of physical memory. So let's take a look at how this happens in a little bit more detail, because I think this is fun. And this also shows you how systems engineering and security engineering is very interesting. And Google folks actually were quite creative in creating this attack. And a lot of later attacks were based on this type of attack, later RowHammer type of attacks, let's say bit flip type of attacks. So I'm going to use the slides that Mark Seaborn presented in his Black at 2015 talks, a fraction of the slides. And basically, this is the description of the exploit they have. So as you know now, also x86 page table entries are dense and trusted. They control access to physical memory. A bit flip in a page table's physical page number can give a process access to a different physical page. Now you can appreciate that, right? If you change the physical page number with a bit flip, you can gain access to a completely different page. Right? So the aim of the exploit they developed was to get access to a page table. And once they get write access to a page table, this gives access to all of the physical memory. When they say get access, they mean write access in the end. They should be able to write to the page table. But of course, it's not easy. They need to cleverly construct the attack, and they wanted to maximize the chances that a bit flip is useful. So what they developed was a technique called page table spraying. They spray physical memory with many page tables so that they can increase the probability of the attack. And they basically try to check for useful, repeatable bit flip first. So basically, first, they try to template the memory, figure out which parts of the memory they can bit flip reliably. And then they spray the memory with page tables. And then they basically try to land a page table to a location that they know is able to, they're able to flip. And that's the idea. So, and this is a copy from their slides. They show a very similar page table entry as I showed you, except this is the long mode. It's basically a 64-bit entry PTE. x86 has many different types of page tables, if you will, because they had support backward compatibility with 32-bit, 16-bit, 8-bit address spaces, etc. But basically, this is what they say. Page table is a 4K page containing an array of 512 PTEs. Each PTE is 64 bits, as we have discussed, right? And there's a physical page base address. So they said they could flip writable permission bits, read write over here, as we have discussed. This is only 1 bit. 1 bit out of 64 gives you a 2% chance. Not so good. But they decided they should flip physical page numbers. It's 20 bits on a 4 gigabyte system. And you get a 31% chance of flipping bits over here. This is 20 out of 64 is 31%, right? Okay, so let's take a look at how they do the attack. So this is the virtual address space. This is physical memory. And then they say, what happens when we map a file with read-write permissions? So file gets mapped over here. As one of you asked the question, what happens when you do a file IO? Part of the file that you're accessing, 4 kilobyte portion, gets mapped to physical memory. What else happens? Well, page tables also get mapped to physical memory. And page table basically provide you read-write permissions and indirection to that file. Okay, now we're going to be clever. What's next? What happens when you repeatedly map the same file with read-write permissions? In the virtual address space, you basically keep different virtual addresses, but they map to the same physical address. But page table entries are different for different virtual addresses. Now we're creating many, many page table entries that map the different virtual pages to the same physical page, because it's the same file in the end. You're just opening it again and again and again and again and again and again, so that you're getting a different virtual address. Okay, this sounds beautiful. What you can do is you can fill the entire physical memory with page table entries, or a good chunk of it. And now you have a lot of page table entries over here and just little data. And each of them points to the pages in the same physical file mapping, and you have read-write access. Remember that. Write access is important over here. Now, if a bit in the right place in the page table entry flips due to RowHammer, the corresponding virtual address now points to a wrong physical page with read-write access. And that happens to house a page table. Chances are this wrong page contains a page table itself, an attacker that can read-write page tables now. And they can use that to map any memory read or write, meaning they can change the page table and they can write to any part of memory, right? Because you have access to a single page table. It doesn't matter what page table it is. You have access to that page table. You can map it to anywhere in memory, which means that you can read or write any content in memory at this point, which means that your system is completely compromised. That's the idea, basically. And this is their exploit strategy. As I've given you that, actually. Now you understand how virtual memory works. You understand how bit flips work. As a result, you know how this works probably, right? Of course, it's security engineering. In practice, there are many complications, as you can see at the bottom. But you allocate a large chunk of physical memory, memory in general. Search for locations prone to flipping first. Check if they fall into the right spot in a PTE for allowing the exploit, because you need to be able to flip the right bits in the PTE. So you need to template the memory to figure out what parts of your memory are actually vulnerable to this sort of bit flips. And they should really be in the right locations corresponding to, let's go back, corresponding to this physical page-based address, basically. But you can do all of that. That's not hard. If you know your system at the low level nicely, it's not hard. And then return that particular area of memory to the operating system, saying, so basically user does this. User allocates the memory, checks the memory, figures out whether it's vulnerable to RowHammer, and then finds a good part of memory and returns back to the operating system. The operating system doesn't know that the user figured out that a part of memory is vulnerable to memory. And then the user is going to be clever. It's going to force the OS to reuse the memory of the page table entries by allocating massive quantities of address space, just like we discussed, by page table spraying. And then it causes the bit flip. It shifts the PTE to point into the page table. And now you can get read-write access to all of your physical memory, and you can abuse it as you want. Of course, it's not easy. There are many complications. And if you're really interested, you can watch their talk and read their blog. And that's why RowHammer is successful, basically, because it's relatively easy to exploit. It's not much easier than Meltdown and Spectre, actually. It's relatively easy to exploit. Okay, I'm not going to go through this in detail. I showed you some of these slides, but there are many, many works that have done similar exploits. And they basically fundamentally do something similar. I'm not going to go through this. Some of them actually leak bits. So some of them allow you to infer bits in some virtual memory location that you're not supposed to have access to. And these are the more neural network kind of works that basically deplete the intelligence of the neural networks, if you will. Okay, so we've discussed RowHammer. If you're interested, you can certainly read more about it. And I think this is fascinating, as you can see. And we have some recent work showing that RowHammer problem still exists. Unfortunately, we need to fix it, and we have some solutions. If you're interested, you can also read them. But I will point out that very recently, this was actually a few days ago, Google provided another blog post and a PDF file also, where they said that they have a new hammering technique for RowHammer that shows that RowHammer is getting worse, in addition to the papers that we have written that I showed you, flashed earlier. They basically show over here that you can have victim far away from the aggressor. These are physical distances. You can have a victim over here, a heavy aggressor over here, and a lightweight aggressor. And by orchestrating the accesses to this aggressor, doing many accesses over here, and a small number of accesses over here, you can actually cause bit flips in the victims over here that are farther away. And they basically say that this is likely an indication that the electrical coupling responsible for RowHammer is effectively becoming stronger in newer technologies, just like the conclusion of our work. But they show another example of how RowHammer is getting worse in real systems. Okay, so I find this fascinating, so I will keep recommending you the RowHammer lecture. And you can find more detailed lectures on RowHammer in our computer architecture class. So takeaway, basically, if hardware is unreliable, higher level security and protection mechanisms are useless, to say it directly, let's say. They may be compromised, basically. So virtual memory provides protection at a higher level. It's great, but if you have hardware faults, you have a problem. This means that the root of security and trust is really at the very, very low levels, at the hardware level, in the hardware itself. So RowHammer, Spectre, Meltdown are recent key examples of this. So what should we assume the hardware provides? How do we keep the hardware reliable? How do we design secure hardware? How do we design secure hardware with high performance, high energy efficiency, low cost, and convenient programming? These are all excellent questions. And we really need to think about this deeply, because as RowHammer shows, and as Spectre and Meltdown reinforce, the real root of security has to be at the hardware. If you have some problem at the hardware level, all of the security mechanisms, protection mechanisms like virtual memory, like we've been talking about, can be compromised significantly. So there's plenty of exciting and highly relevant research questions over here. And if you're interested, certainly you can go further. In the epilogue part of this lecture, I will tell you more about some future directions. Okay, I think this is a good place to take a relatively short break. This time, sorry, I'm going to give you an 8-minute break because I want to really finish virtual memory and give you some idea of epilogue. But we're almost done with virtual memory. We're going to cover some issues in a little bit less detail. Well, some interesting issues and open up some questions. And then we're going to conclude with a real system example. And then we're going to do an epilogue. But let's take an 8-minute break right now. And we will be back at, I guess, 15:26. Okay, I think we can continue. I'm going to delete this lecture break slides. Now we're going to talk a little bit more about issues in virtual memory, but some of which we've already talked about. So these are some extra slides for your benefit. I'm going to go through some of them quickly. But we already discussed how large is the page table and how do we store and access it. I'm going to give you a little bit more example from real systems with some additional slides, but we're going to skip some of the slides. The second question is, how can we speed up translation and access control check? Again, we've discussed this, TLBs. But again, these are very important. That's why I raise up these questions. And then there's a third question, which was brought up by one of you in the last lecture, I think. When do we do the translation in relation to the cache access? And that's going to be important. I'm going to give you a teaser of that, but we're not going to go into the details. There's some backup slides and some lecture references you can take a look at. There are many other issues in virtual memory that we will not cover in detail. I mentioned some of those actually while we were discussing some earlier issues. What happens on a context switch? How can you handle multiple page sizes in an efficient manner, etc. We're going to touch upon some of this when I give you a real world example, but not in great detail. So issue one is, how large is the page table? Where do we store it? In hardware, physical memory, virtual memory? I think we've already discussed these questions. With multi-level page tables, part of the page table is in physical memory, and the rest is in virtual memory, and some of it is not allocated also. And how can we store it efficiently without requiring physical memory that can store all page tables? And the idea is multi-level page tables, as we have discussed, right? And this is the slide that I'm showing you for the fourth time, perhaps, because we have seen it in the last lecture also. And we've already discussed the solution. And we discussed how to do the page table access. There's a page table base register. There's also a page table limit register so that you don't exceed the virtual memory that you're accessing. If virtual page number is out of bounds, it exceeds the page table limit register, then the process did not allocate the virtual page. So there's an access control exception that happens based on that as well. So there's hardware checks. x86 actually has segmentation also, as we discussed in the last lecture, which is a different level of protection, but it's not as important today. That's why we don't talk about it as much. Okay, we already discussed that page table base register is a part of process context. It's an architectural register, and it needs to be loaded when the process context switched in. If you don't do that, then you have a problem, basically. And it's the hardware's job to do that. If you don't do that, actually, the process will be using somebody else's page table base register, and you basically compromise security and privacy right away, right? So the hardware bugs at any level of this process can directly affect your security and privacy, basically. Okay, I've already given you these examples. I'm actually going to skip to the page table entries that are more, so these are more recent. This is x86-64. You can see that page table entries have increased to 64 bits. So they used to be 32 bits over here. Each of these are page table entries. And you can see that now they're 64 bits. Why? Because we need to be able to address larger and larger virtual and physical memories. And so you can see that there are different types of page table entries, CR3. There's possibility of 5-level paging in x86-64. So this is a 5th level, which is they don't call it the directory anymore, of course. This is the 1st level if you have 5th level. This is the 1st level if you have 4 levels. And you can see that there are 1 GB page frames also. So there are 3 types of pages in x86 right now: 1 GB, 2 MB, and 4 kilobytes. And you need to choose which page you want. This is a tough choice, not an easy choice, or the system needs to choose for you what type of page they want. And again, it's a tough choice, basically. It depends on your locality characteristics and your translation, right? And you can see that the other flags also exist. There's nothing special that I want to provide over here, other than this is the 4-level paging example that I showed you earlier, right? We're not going to go through this again, but existing systems are complicated multi-level page tables. This is 4-level paging for 4 kilobyte pages, I should say. This is 4-level paging for 2 MB pages. So it's, and this is 4-level paging for 1 GB page. So clearly for 1 GB page, you actually don't have 4 levels, right? You have 2 levels over here. And you have 3 levels for 2 MB pages, but this is the 4-level paging is the name of the paging mechanism that they use. That's why it's called all 4-level paging. The maximum levels is 4 with the smallest page size. Okay, so that's how large is the page table and how complicated it gets, basically. So how can we speed up the address translation and check? We already know about translation look-aside buffers. We've already talked about how to make it fast. Let's talk about who manages it, meaning what if you miss in the TLB? So TLB caches the recent access translations, the recent translations, but what if you miss in the TLB? What TLB entry do you replace? Clearly, it's a caching decision. Who handles the TLB miss? Hardware versus software. And there are advantages and disadvantages to this. In many systems today, hardware is increasingly handling the TLB misses, but there are actually some systems that handle the page TLB misses in software, like MIPS actually handles TLB misses in software. And that gives more flexibility to the system. And we're going to talk about the trade-offs. And then what should be done on a page fault is, what if you actually find out the PTE eventually and figure out that it's a page fault? Then what virtual page do you replace from versus physical memory? These are different events. I want to emphasize that TLB miss is very different from page fault. TLB miss is that says that the translation is not cached in the TLB, in the hardware TLB. Page fault means that the physical page corresponding to this virtual page is not mapped in physical memory. It doesn't exist in physical memory. So you need to bring it. You may get a TLB miss that doesn't result in a page fault, obviously, right? You can actually have a valid page table entry. You may get a page fault that doesn't result in a TLB miss. That also happens if the page table entry is cached in the TLB, but it becomes invalid for some reason. And there are reasons for it, for TLB coherence reasons, for example. When you, for example, replace the page that is subject to the translation, you may actually invalidate that TLB entry. It depends on how you invalidate exactly the TLB entry, of course. But this is certainly possible also, depending on how you implement things. But it's more rare, of course. So who handles the page fault? It's usually the software, basically. Hardware can potentially accelerate it. But so actually, I should say it's cooperative, but it's done under the supervision of the software, basically. You usually have an exception that leads you to a software handler, and the software handler decides what to replace and how to handle the page fault. Usually, hardware handles the TLB, but not always. Okay, we already discussed the TLB. This is a more generic explanation, so you can take a look at it. But basically, the TLB is small. It cannot hold all PTs. Some translation requests will inevitably miss in the TLB. So you must access memory to find the required PTE. This is called walking the page table. Essentially, you walk all levels of the page table in a multi-level page table to get to the PTE, page table entry you're looking for. And this takes a long time, as you know, right? There's a large performance penalty. So better TLB management and prefetching can reduce TLB misses, just like better cache management and prefetching. But then eventually you get a TLB miss. Who handles that TLB miss? Is it the job of the hardware or software? Meaning, whenever you get a TLB miss, do you take an exception or does the hardware handle it? So there are multiple approaches. It's hardware managed in most systems today, x86, ARM, etc., for example. And hardware does the page fault. Essentially, it walks through all of the page table accesses, and it fetches the PTE in the end and inserts it into the TLB. If the TLB is full, the entry replaces another entry. It's basically you do the replacement. And it's done transparently to the system software. This way, you can employ specialized structures and caches, for example, page walkers and page walk caches that we will see in an example soon. Approach 2 is software managed. MIPS, actually, the architecture that you are implementing, does it, except you're not implementing the virtual memory part. The hardware raises an exception, and the operating system does the page walk using some instructions. You can clearly do that, right? You can clearly construct instructions to access page tables, and the operating system fetches the PTE, and the operating system inserts and evicts entries in the TLB. Essentially, this is software managed TLB. And clearly, there are trade-offs to this approaches, and you can imagine some of the trade-offs. Hardware managed TLBs, there's no exception on TLB miss. Instruction just stalls. Other instructions may already be going on in an out-of-order machine. That's great. Independent instructions may continue. And there are no extra instructions, data brought into caches. You don't do a context switch to a software. So that's the big advantage. And that's why hardware managed TLBs are commonly used today. But then the downside is page directory and table organization is etched into the system. The hardware needs to implement that. And if you change it somehow in software, your hardware that manages the TLB is useless now. So OS has little flexibility in deciding the TLB organization and page table and directory organization. Software managed TLB, of course, doesn't have that disadvantage. The OS can define the page table organization independently of the hardware. And it can also employ more sophisticated TLB replacement policies. The downside is performance overhead. You need to generate an exception, and you need to flush the pipeline, execute the exception handler, and extra instructions are brought into the cache. Of course, you could handle this in another thread. So you may actually eliminate some of the performance overhead, like the pipeline flush, but still there's overhead in executing other instructions to actually handle the software managed TLB. In hardware, if you handle it, you can have a specialized structure completely, as we will see in Intel systems soon. Okay, the final issue that I'm going to briefly touch on is when do we do the address translation in relation to cache access? And this becomes important, especially from the perspective of the L1 cache. Because at the if you need to do the translation to access the cache, now translation is on your critical path, right? Critical path of cache access. So this is a teaser. When do we do the address translation? Do you do it before or after accessing the L1 cache? And in other words, is the cache virtually addressed or physically addressed? And this is a fundamental choice at the L1 level. But you could also potentially move it to the L2, L3 levels, but it doesn't make sense fully at some point. And then the difficult question is, what are the issues with a virtually addressed cache? And there are issues. And one issue is synonym problem. Basically, two different virtual addresses from the same process or different processes can map to the same physical address, which means that same physical address can be present in multiple locations in the cache if you're actually using virtual addresses to address the cache. And this can lead to inconsistency in data because the same physical address in different multiple locations, let's say different sets, different indices in the cache. And if one of them is updated, the other one needs to be updated also or invalidated. So you have a coherence or consistency problem inside your own cache if your cache is virtual, because two different virtual addresses can map to the same physical address. There are other problems, actually. This is one problem. There's also a homonym problem, which is the fact that same virtual address can map to two different physical addresses. Why does this happen? Because virtual address can be in different processes, right? The same different processes have the same have the virtual address space to each of them, and the same virtual address can be mapped to different physical addresses. And this becomes a problem when you're managing the cache if it's completely virtual. So usually the solution to fix the homonym problem is to introduce address space IDs to distinguish between different processes and address spaces. This is easier to solve at hardware cost. Synonym problem is different virtual addresses can map to the same physical address. And again, why? Different pages can share the same physical frame within or across processes, right? Essentially, different virtual addresses can map to the same physical address. Just like we saw in the Google example, right? Different virtual addresses map to the same file, which is mapped to the physical memory. And many different virtual addresses can map to the same physical address. And there could be many reasons. Shared libraries, shared data, copy and write pages within the same process, files that are mapped. That's part of shared data, actually. And then the question is, do homonyms and synonyms create problems when we have a cache? And is the cache virtually or physically addressed? Becomes a very relevant question over here. And there are ways of solving the synonym problems also. I'm not going to go into detail. I have some backup slides for this, but I would like you to think about it if you're interested in this. So there are three ways of designing the first level cache. It could be physical, meaning it can the access of the cache happens after the virtual to physical address translation. You don't have the homonym and synonym problems, but you have a huge latency overhead. You need to access the cache, you need to go through TLB. And we discussed that first level cache is very latency sensitive. So you don't want to do that. In general, this is not done. The second option is you access the cache completely with virtual address and then do the translation. This is completely virtual, so there's too much flexibility and there's too many homonym and synonym problems because of this. As a result, this is also not done in general. Usually you do a compromise that looks like this, a virtual physical cache or virtually indexed, physically tagged cache, where you access the cache concurrently with the TLB, and then you do the tag check using the physical address. Now, for this to work, you need to design your cache carefully such that the indices, the virtual index, doesn't change during translation. So you should really not index the cache using part of the address that's going to change using the translation. Otherwise, you may actually map two different virtual addresses, two different virtual addresses that map to the same physical location to different locations in the cache. So if you didn't understand that, that's okay. But if you understood it, that's good, because that means that you've actually been really following what's going on in virtual memory. But think about what happens in this case. What kind of bits should you use for the index into the cache? And what can you do and what can you not do? So the idea is virtually index the cache, but do the tag comparison in the cache using physical addresses, because you will have the physical address at the end over here. Okay, and usually systems employ this sort of caches, virtually indexed physically tagged cache at the first level. The problem is not present in the lower level of the hierarchies, because at that point you already have the physical address. You'd better do the TLB translation before the second level, for example. Okay, see backup slides for more. Let me now quickly go over a modern virtual memory system in Intel Skylake, and then we're going to transition to the Epilogue part. So this is address translation has evolved a lot. So this is simple address translation in earlier systems. You have an L1 data, an L1 instruction TLB, L1 data cache, which is not part of your translation system, but usually you do it concurrently with the L1 data cache, as we discussed. And then there's a software page table worker like MIPS. Modern address translation is much more complicated. Modern MMU, you can think of this as MMU. You have L1 and L2 ITLBs, L1 ITLB, L1 data TLB, L2 TLB, page table walker, hardware, page table walker cache to cache the middle levels of the page tables, multi-level page table. So there's a lot that goes on. And then there's also clearly the cache. So a memory management unit, we discussed it. It's responsible. It's the hardware that's responsible for resolving address translation requests. It's 1 MMU per core, usually. MMU has 3 key components, TLBs. We know what TLBs are. Page table walk caches. They essentially offer fast access to the intermediate levels of a multi-level page table. So TLBs cache PTEs, not the intermediate parts of the page tables, but page table walk caches cache intermediate mappings at the hierarchy, page table hierarchy. This is to aid the translation TLB misses, essentially. And then hardware page table walker that sequentially does the page table walk that accesses the different levels of the page table to fetch the required PTE. And this is all in hardware. So now we can see that there's a big hardware over here. Okay, let's take a look at this MMU. Let's tear it apart in an Intel Skylake system, which is reasonably new. L1 data TLB, essentially, even this is complicated. Basically, they have 3 TLBs, each for different page sizes, 4 kilobyte, 2 megabyte, 1 gigabyte. And you can see the entries over here. There's only 4 entry 1 gigabyte TLB and fully associative. But this, you can address 4 gigabytes of memory with this. That's why it's 4 entry. 2 megabytes, 32 entries, you can address only 64 megabytes, right? With all of those. The 64 entries, you can address only 256 kilobytes, I guess, in this case. That's too bad. So this TLB is actually quite powerful. Even though it has fewer entries, it's very powerful because it really spans a 4 gigabyte portion of the physical memory. Okay, virtual memory, I should say, but also physical memory. I mean, if you think about it from that perspective, right? And virtual to physical mappings are inserted into the corresponding TLB after a TLB miss, clearly. And during a translation request, all 3 L1 TLBs are looked up in parallel. So now you can see that it's complicated. And having multiple page sizes clearly complicates the picture. And Intel folks did not design a single TLB with different page sizes because they thought it was easier to design 3 TLBs with different page sizes. And you can imagine, this is a cartoonish picture. You need to basically index these TLBs with different parts of the virtual address and do the tag match, etc. And then decide which one you hit on. Okay, so there's an L2 unified instruction and data TLB. Essentially, L2 unified TLB cache translation for both instruction and data. It's still private per individual core. And there are 2 separate L2 TLB structures now. One for 4 kilobyte and 2 megabyte pages, and one for 1 gigabyte pages. And you can see that these are bigger. But again, they decided to consolidate 4 kilobyte and 2 megabyte together. So the design of the TLB is a little bit more complicated for this one. Okay, but these are bigger, as you can see, and you can see the penalties. Of course, the question is, how can you support both 4 kilobyte and 2 megabyte pages using a single structure? There's not enough detail on this, but you can imagine, we discussed this actually when we talked about associativity in time. You basically index the TLB once using a 4 kilobyte index. And then if you miss, you index the TLB again. Okay, that's the idea basically. There are 2 steps basically. In time, you index the TLB assuming different page sizes. Okay. If you hit in the first step, that's good. Then it's a 4 kilobyte page. If you miss in the first step and in the second step, then it's a 2 megabyte page. If you miss in both, then you need to do the page table walk. The general algorithm is to recalculate the index and probe the TLB for all remaining page sizes. And we've seen this in associativity in time. If you remember the cache lectures, we said pseudo associativity. This is poor man's associative cache, if you will. We have associativity in space normally, but now we have associativity in time. We change the index and index into the cache again and again and again. And you can do it many, many times to get very high levels of associativity or support any number of page sizes. And this is the example basically. You first calculate the index for 4 kilobyte. If you miss, you calculate the index for 2 megabytes. Okay, so L2 TLB has n-step index recalculation. This is simple and practical. The downside is TLB hit latency is longer and varying. And now you have slower identification of L2 TLB miss as you need to basically probe all page sizes. So potentially you can optimize it by making the lookup parallel. Of course, this adds hardware cost. Or you can predict the page size, predict the probing order. And trade-offs are again similar to associativity in time versus space. Okay, let's talk about the hardware page walker components. As we said, TLB misses are handled in hardware. And this is an interesting component, complicated component, that walks the multi-level page table to avoid expensive context switches and software handling of TLB misses. It has two components. One is a state machine that is designed to be aware of the architecture's page table structure, and then registers that keep track of outstanding TLB misses. So I'm not going to go into the details of it, but you can imagine how the state machine walks the page table. Of course, we actually saw the slide earlier. This avoids the need for context switch on a TLB miss. It also has the ability to overlap TLB misses with useful computation, as we discussed. It supports concurrent TLB misses, because in hardware, you can support many concurrent misses. But of course, there's a downside: hardware area and power overheads. And now the software cannot change the page table organization and properties, if you will. It's etched into the hardware. Okay, so how do you do this walk? I'm not going to go through this in detail, but you start with CR3 register and then concatenate CR3 with the virtual address, and then you essentially do the walk of the multi-level page table that we discussed earlier. So it takes time, basically. Okay, but of course, there's benefit to it. That's why it's implemented in real processors. It allows overlapping of many TLB misses with useful computation. So if you do the software TLB mishandling, you need to context switch to a TLB mishandler, and then you do a load B. You cannot handle this TLB hit because you have a context switch, right? Hardware page table walk, TLB miss. Concurrently, you can handle other TLB hits, so you can do out-of-order execution, and you can get the full benefits of out-of-order execution, etc. Right? So you save a lot of cycles actually with hardware TLB mishandling. It's also called a page table walk, basically. Okay, finally, to aid this hardware page table walk, there are page walk caches. As we discussed, it's different from the TLBs because TLBs cache the page table entries, the leaf nodes in the last level page table. Page walk caches cache stuff, going back to this picture, from essentially all of these other levels, not the real page table that you're looking for. Why? Basically, you want to speed up the hardware page table walk. That's the idea. I already said all of this, actually. These are low latency caches that provide faster access to the page table levels so that the page table walker does not have to access memory or the cache hierarchy for every page table walk. It can just access these page walk caches, okay? And that's the Intel Skylake MMU for you, basically, in a nutshell, very quickly. And actually, there are other virtual memory designs. This is Apple A14 over here, based on some reverse engineering, etc. But you can see that L1 TLB and L2 TLB are larger in Apple A14, and also the page size, the default page size, is actually larger. I'm not going to go through the details of it, but you can enjoy the slide on your own. Okay, so we're at the end of virtual memory. So to summarize, virtual memory has a lot of benefits. It gives the illusion of infinite capacity. And we already discussed everything, so I'm not going to go through all of this again. This is a summary of everything we discussed. But it provides you the illusion of infinite capacity. It also provides you protection. That's very important. And there are a lot of issues that we need to solve along the way. And those issues all exist in real systems, and they're solved in some way. But there's more, which we're not going to talk about. How do you handle virtualized systems? Pose the problem. I'm going to flash a slide related to this. You may have virtual machines and hypervisors running programs, orchestrating systems. Now you have another virtualization layer. And that actually increases the number of virtual memory translations that you need to do. And existing systems provide support for that, called nested page walks, for example. I'm not going to talk about that, nested TLBs. There are alternative page table structures that we did not talk about. Inverted page tables, we briefly mentioned when you want to actually, the operating system may store the reverse mappings from physical pages to virtual pages to figure out what to replace. Some systems actually have inverted page tables to begin with, probably a bad idea, but there are trade-offs associated with it because inverted page tables are actually quite compact. In terms of storage size, these are small. Hashed page tables can enable fast access to the page tables. Actually, this may be a good idea to revisit in many systems, which we did not talk about. Basically, we just directly indexed. We didn't really do sophisticated hashing to the virtual address. And there's more that we don't have time to cover. But I will show you the one picture over here, which is the virtualized system. You may have a virtual machine, for example, like VMware. You may have a guest OS running on a host OS, running on the physical CPU. And this virtualized environment needs to have an additional level of address translation from the guest OS virtual address to the host OS virtual address. And then host OS virtual address needs to be translated to the host OS, the CPU physical address, essentially. And that requires another level of layer of translation, if you will. And this leads to a lot more memory accesses, basically. I'm not going to go over it, but it's a lot of memory accesses. And existing hardware, x86 hardware for sure, provides support for directly translating from the guest virtual address to the host physical address, while trying to avoid as much as possible this indirection level. So that's a direct support for virtualized systems. Okay, so let me conclude with this parting thoughts, the virtual memory part, and then we're going to have an epilogue for those who wish to stay in the rest of the lecture. But virtual memory is actually very important because it's one of the most successful examples of multiple things. Architectural support for programmers, how to partition work between hardware and software. So it's really hardware-software cooperation, which is similar to what I said over here. And it's a very successful example of the programmer-architect trade-off. It basically makes programmers' life super easy, architects' life, both system architect and micro-architects' life harder, as we have seen. But it is one of the most successful examples. But going forward, how does it scale into the future? It's not doing very well, in my opinion. And there are a lot of papers that are written on it. I'm going to show you some pictures of it also. But basically, we have increasing huge physical memory sizes, both local and remote. And 256 terabytes are starting to sound small for our memory sizes, basically, because data is huge. We have hybrid physical memory systems, DRAM and VM SSDs, and we want to increasingly manage everything using a single memory abstraction. There are many accelerators in the system addressing physical memory. They want to be part of the virtual memory. And there are virtualized systems, like I showed you earlier, hypervisors, software virtualization, local and remote memories. So how does it scale into the future? So the management is actually quite complex overall. So it's not going to scale very well. So there's one question. In case of hashing, will the synonym and homonym problems be reduced? Not necessarily. That's a very good question, but not necessarily. Basically, you still have a virtual address and you still have a physical address. It's just a way of determining the mapping. Okay, so if you want to learn more about rethinking virtual memory, we do a lot of that in my research group, actually. And this is one of the papers that we have written last year that rethinks virtual memory from different perspectives. You can also watch a lecture related to it. This tries to solve the rigid page table structure problems, translation overheads, which we have discussed many times, and heterogeneous memory management. But if you're interested, we're not going to cover it. You can take the future lectures or also read the paper. And there's a lot more in virtual memory. Like if you want to know more about the synonym and homonym problems, we cover that in other lectures, but we don't have time to cover it in this lecture. But you can also watch lectures. As you can see, there are multiple solutions to the problem. Okay, there are more lectures on virtual memory that I'm not going to go over right now. But hopefully this gave you a reasonably comprehensive overview of issues in virtual memory, which I think is critical to get exposed to as early as possible in your career, because it is a lot of cool ideas. It is a lot of complexity at the end, but it's one of those things that has been successful despite the complexity, heavy complexity, because it makes programmers' life easier. Okay, feel free to ask more questions. I'm going to skip to, the final lecture, if you will, which is the epilogue. There's really no required material over here, except for an announcement in the middle somewhere, but you can also get that announcement somewhere. So if you don't need to be here or don't want to be here, you can feel free to hang off. But if you want to continue, again, feel free to continue. But you can also ask questions from the virtual memory lecture. This may be better titled Epilogue and Introspection, because we're going to do some introspection into what we have covered in the earlier parts of the course also, because we have covered a lot. And I think you should be proud of what you've learned, and hopefully you've learned the basic principles of a lot of things, which is the most important thing. Okay, there are no required readings for this lecture. That's the good part. But basically, remember, I showed you the slide in one of the earlier lectures, the major high-level goals. We wanted to understand the basics, principles, and precedents, and hopefully we covered a lot. Like virtual memory actually shows you a good chunk of that, right? We're giving you a lot of that. And based on such understanding, hopefully you've learned how a modern computer works underneath. And hopefully we've taken an approach where you can critically evaluate the trade-offs of different designs and ideas. If you've been following, you probably know that I never dismissed a single idea saying this is bad or this is good. I gave you the good side and the bad side, and then I potentially made a judgment call saying, okay, this didn't work out well in practice because of this reasons, right? Usually because of the downsides that we discussed. So all ideas have upsides and downsides, and it's really important to be able to critically analyze those upsides and downsides. And that's if we have achieved that in this course, then I'm happy, basically, because that's perhaps the most important part of the course. So your critical thinking, your critical analysis skills. And it happened to be that we apply those critical analysis skills to ideas in computer architecture and digital design in this particular course. But those skills are applicable way beyond this course. They're applicable to any aspect of life, actually. If you've got that critical thinking skills and reinforced it in this course, then I'm happy. And we've implemented principled design, a simple microprocessor with all of its idiosyncrasies, and you've done it in FPGAs with all of the FPGAs idiosyncrasies. So hopefully you learned from that exercise a lot. And hopefully you learn to systematically debug increasingly complex systems during your labs as well. And hopefully some of you have actually been developing ideas. Maybe some others have been developing ideas and they have not been vocal about it. That's perfectly fine. But hopefully this course has set the stage so that you can develop new out-of-the-box designs and solutions to problems. Remember, we started with solutions to problems in the first lecture. Computing is all about solving problems. So hopefully we've actually achieved that as well. So, I mean, again, this is a slide from the first or second lecture, I think. The focus was on basics, principles, and precedents, and how to use them to create and implement good designs. And I think over the course of 26 lectures, we've covered them. Okay, why these goals? Regardless of your future directions, hopefully these principles will be useful for you, as I said earlier, in doing many things. Whatever your path is going into the future, and you're the only one who can choose that path, of course, potentially with guidelines from other people, of course. But whatever you choose in this list over here, design better hardware, software systems, make better trade-offs in any design, solve problems better. It could be any problem. Think in parallel and think critically. Hopefully this course helped you. And as I said, the last three are the most important, perhaps. I mean, these things hopefully you understood, but the last three are the more generally applicable skills going into the future. Solving problems, thinking in parallel, and thinking critically. And we've come a long way. If you remember, we started the transistor as the building block. We now built up to virtual memory and system software mechanisms, and also security attacks, if you will, that circumvent some of those mechanisms. And then in the meantime, we covered logic design, execution models, von Neumann model, ISA, microarchitecture, many key processing paradigms that I'm going to flash in the next slide, and the memory system and the memory hierarchy. So hopefully there are three takeaways I would like to derive from here. All we covered is real and used in real systems. At some point, it was used in real systems, and it's increasingly important because a computer architecture is becoming increasingly important. Principles we covered apply broadly. I think I hammered this home. And trade-off analysis and critical thinking that you're exposed to apply even more broadly than the principles of individual discussions. Okay, and recall, I showed you this when we started the memory lectures. We're done with this part of the lecture, and this doesn't even cover the first part of the lectures, like digital design. And we covered, you're familiar with many processing paradigms right now, and there are a lot of trade-offs associated with them. Hopefully you're thinking about them. And now you're also very familiar with memory systems. We actually came a long way understanding the memory systems, which many introductory courses do not do, which is a bit sad in my opinion, because memory is the biggest bottleneck today, as you probably know. But now we are also familiar with many aspects of memory systems, and hopefully you can think of trade-offs for many different system designs and ideas. And we also covered the computer architecture from a broad perspective. Clearly, we focused on the hardware-software interface and microarchitecture and logic, but we also covered issues related to system software, languages, and algorithms through different lectures, GPU lectures, SIMD lectures. Right now in the virtual memory lecture, for example, a good chunk was system software, but caching lectures and other lectures also. So essentially, hopefully this was a learning and growth experience for you. What we saw in this lecture, in the course of 26 lectures, actually changed the world, and it endured the test of time. A lot of the ideas that we discussed actually has enabled many revolutions in computing, like machine learning revolution being one of them, right? We talked about GPUs, SIMD engines. We talked about systolic arrays. And it will be even more important going into the future. You may not all be future architects. You may choose to be, that's fine. You may not all be system designers. You may decide not to do computer science even going forward, but hopefully your development and thinking can benefit from the way we analyze the concepts, trade-offs, principles, and the critical thinking that we apply to things. And our focus was really on understanding, learning, and critical analysis, as opposed to like number crunching. I mean, some of the homework exercise, you have to do that so that you can understand and reverse engineer. But I believe all of these are agents for your growth, understanding, learning, and critical analysis. And the course was specifically constructed to activate these agents so that hopefully they're activated lifelong, because I don't think any of these end with any education level, for example. Education is continuous for lifelong, and understanding, learning, and critical analysis is really important. And hopefully you have those agents. So let me talk about what we did not cover and also look into the future a little bit. The computer architecture is very rich. There are many ideas, much creativity, many trade-offs and problems. And hopefully we've exposed you to some of them, a good chunk of them. But as scaling, performance, energy, reliability, and security issues become worse in everywhere, computer architecture will become more and more important. I mentioned this in the first lectures. Maybe at that time you didn't have the background to fully appreciate it. Maybe you may want to watch those lectures again. But now circling back to this, hopefully you understand what I mean. This is already obvious in the accelerators that are being designed. I'm going to show you a little bit more examples actually, because things happened in the last few weeks in AI ML accelerators. Hardware security issues that we've discussed, like RowHammer, things happened last week in RowHammer. Novel execution paradigms like processing in memory. I'm going to talk a little bit more about that. In fact, I'm going to assign you a review assignment related to that. So this is going to be your review assignment. Basically, this is a lecture that I recently delivered that covers some cutting edge topics in processing in memory, but more data-centric, data-aware and data-driven architecture. So again, this is not a required assignment, it's an optional assignment, but you get 1% credit for it. And hopefully you'll learn about some processing in memory issues, some cutting edge issues in processing in memory. And I would recommend doing that, but you don't have to do that if you don't want the 1% credit. But 1% credit is nice, of course, right? Okay, so that's the optional assignment. Watch the lecture and analyze it critically. And it's very similar to the first assignment that you have done, and actually all three assignments that you've done. Hopefully you'll have a critical summary with the positives and negatives and your key takeaways. And I made this due June 20th, but we can also extend it if really needed. Okay, and if you want to watch a longer version, we have lectures on memory-centric systems that I mentioned earlier, and this is the longer version. So if you prefer to actually go deeper, you can watch the longer version also, but this is not as up-to-date as that earlier one. Okay, so going forward, I think architectures for machines that we're going to increasingly rely our lives on need to be more data-centric, data-driven, and data-aware, because data is increasing in systems. I'm going to talk about this a little bit more in the second part of this. So we really need to rethink how we design architectures, because the processor-centric architectures that we have discussed in most of this course is not scaling very well, because everything is about data, and we have a huge memory problem. And we have a huge memory problem because of the way we are designing things. The processor-centric design paradigm is not working well. I'm going to talk about that. But essentially, people have been also trying to make things more intelligent, imitate neural networks, machines like this maybe, and try to create artificial intelligence. And it's not an easy task. We really need to think more about how we understand and design architectures. That's one of the reasons why it's an exciting time to be understanding, designing computing architectures. There are many challenging, exciting problems that no one has tackled or even thought about before. We're actually really scratching the surface, I think, in intelligence, for example, and how to design systems for intelligence or genomics. And all of these can have a huge impact on the world's future. If you have a huge security problem, you can have a bad impact on the world's future. If you have a completely secure system that can provide you completely good self-optimizing, self-driving system, for example, now you can have a huge impact also. And clearly, there are many drivers for change. But these applications, as we discussed in earlier lectures, as people dream, new applications, new systems will come, and they will be formed, and data will be increasing in the systems. Of course, we should really be cognizant about how sustainable and efficient we can make computing, right? And that also relates to the significant difficulties at the technology layers. There are energy problems that we're facing, reliability problems, complexity, security, scalability problems we're facing at the lower levels, as well as at the higher levels. Of applications that we want to, problems that we want to solve, essentially, huge problems that we want to solve. And all of them go through designing better architectures, better systems. And I think this course is very fundamental to in introducing you to how to start solving some of those problems. Okay, so as I said, this is a great time to be a computer architect because a lot of things in the system is strained. Applications are more demanding. There are many requirements. There are multiple possibly emerging technologies, many issues, and many big problems waiting to be solved. And many big innovations require computer architecture going into the future, as we have been seeing in systems. And remember, I showed you actually many interesting things are happening today in computer architecture in the first lecture, lecture 1 of this course. Now, many interesting things actually happened during the course of this course. I'm not going to cover all of them. I'm going to show you a few. This thing, for example, happened last week. I think last week. I don't know the exact date, but we have not discussed it. So far, I've shown you systolic arrays. And in the systolic array lecture, actually in the first lecture also, we talked about TPUs, saying that we will talk about systolic arrays. This is Google's tensor processing unit, and this is version 4. They released it recently. They don't have a lot of detail about it, but they want to target even bigger machine learning applications compared to TPU3, which we talked about. Computer vision, natural language processing, recommender systems, reinforcement learning that plays Go like AlphaGo. So they have specialized acceleration mechanisms in the entire system. And you can see that their computation capability is much larger, partly because they have a lot more memory also in this, which they don't disclose. Computation capability is 250 teraflops compared to 90 teraflops in TPU3, which we have seen. And per board, you can get 1 exaflops. So this is amazing. This is, of course, this is one specialized, very specialized accelerator. And you know exactly what principles it's based on, right? Systolic arrays plus very high bandwidth memory, right? And of course, the mechanisms to orchestrate the data movement between the memories and the systolic arrays. And then you can do a lot of matrix multiplications over here and achieve 250 teraflops in this particular device, right? And we have seen TPU3, that was bigger than TPU2. And we have seen TPU2, and we have seen TPU1, right? So these things we have seen, but TPU4 was introduced last week, essentially. So as we actually take this course, go through this course, things are happening. So things are advancing so fast. It didn't used to be the case, basically. In the 1990s, early 2000s, you wouldn't see a processor being introduced once a month even, or once a year, actually, right? Now things are moving much fast because we need to keep up. We need to solve the big problems. Hopefully they're doing it for a good reason, of course. I'm assuming that they're doing it for a good reason. But as I also said in the first lecture, technology is agnostic to your purpose, right? It could be used for good or bad, and hopefully we can use it for good. And this is what happened also in the last few weeks. This is Cerebus's wafer scale engine, and I've shown you before, so I'm not going to go over it. But this is also a big improvement compared to the previous wafer scale engine. And you can see that transistors are increasing, clearly. Moore's law, at least, is partially alive. I believe it's alive, and if people are going to push forward, as long as it can stay alive, it's going to stay alive. And this is one example of it, basically. And finally, this was announced actually earlier this week. This is AMD's last level, 3D last level cache. Actually, we have shown this picture. This was AMD Ryzen from 2020. You can see that most of it is cache, and we said it was 32 megabytes shared cache. What they did was they added more shared cache, except they didn't put it on this die. They put it on another die that would fit on top of the processor die that we have seen, essentially. That's the idea over here. So they increased the size from 32 megabytes to 96 megabytes. So they have an additional 64 megabyte L3 cache stacked on top of the processor die. And it's connected using two silicon vias that go up 3-dimensional. And they get very high bandwidth also into this cache. Not as good as the cache that is on die, of course, but it's still quite good. But the capacity of your cache is very highly improved right now, as you can see. And this was introduced, I think, earlier this week. And you can see that these things are happening. And this is 3D stacked architectures. They're coming, as you can see. We can 3D stack different chips on top of each other. So we're not limited by the 2 dimensions anymore. I think increasingly we're going to see systems like this. And increasingly systems will be more monolithic going into the 3rd dimension. Okay, there's one question. How have they solved the problem with the heat? So that's a great question. Basically, I think I'm not sure. There's not enough description in this announcement. But yes, whenever you go 3D, there's heat and thermals, and they need to have some sort of solution. But probably we will learn more. In the end, I think there's no magic. Either you need to have a better cooling system, which I doubt that they have increased the cooling significantly, but probably maybe they have a higher power budget, etc. Right? But it remains to be seen. Very good question. But there are many, many other ideas that we're not going to talk about and that we didn't get a chance to talk about. I mentioned some of them, but we really didn't delve into the details of it. For example, self-optimizing architectures, using machine learning principles to design controllers, caches, etc. Make the architecture self-learning and self-optimizing as opposed to having heuristics that are designed by humans. Processing in memory systems. I'm going to talk about this briefly as we segue into the future. But emerging memory technologies, I introduced phase change memory a little bit, but we didn't really go into a lot of detail. Solid state disks, interconnects, which is a missing part, and many other issues over here that I'm not going to talk about. And a lot of this is covered in advanced computer architecture courses and the seminar courses that I'm going to mention later on. But a lot of the things, actually, these things were criticized in the past, right? The 3D caches, for example, saying that these are high cost, but they provide you a principled design in some way. And in a sense, they're similar to this Oculus in New York City that I used in my earlier lectures. So if you have principled designs, they may come at a cost, and they will come at a cost, but over time, the cost will amortize itself. So it's really important to think about principled designs and push forward and make our systems better and better going into the future. And we will not regret it as we do that, because we can solve more and more problems. Of course, we need to be careful and efficient while doing that. And if you go and visit Oculus, please send me pictures. I've seen many pictures from many earlier students from this course, because they like some of these architectures. I think anyone who goes there likes it as well. Okay, let me quickly recall some things. We talked about run-ahead execution in the last lecture. This is something dear to my heart, but you can actually do things like this also. So run-ahead execution is an idea that I developed in my PhD, and it's, I'm not going to go through the idea again. You can watch the last lecture clearly, but it's a way of getting the benefits of a large instruction window by not stalling, actually. Instead of stalling, when you get a long latency cache miss, you do pre-execution based prefetching speculatively completely, so that you can parallelize cache misses, prefetch them inside the caches, and you save cycles. And clearly, this has a lot of benefit, and I'm proud of it, given that I've done my PhD on it. And it has enabled, it has been used in systems. And you can see some systems that have been using it. And we mentioned this last time, right? Prefetching and run-ahead execution is employed in IBM Power 6. It's employed in Denver, and in some systems that are not public also, actually. But they are not going to be public for a while, I think. But basically, you can see that there's a lot of benefit to these ideas. And clearly, you can do more readings and watch more lectures about it. But my point is that you can actually come up with these ideas also. Now you have the basics. If you critically think about the problems that we really need to solve in our systems and architectures, you can solve those problems in innovative ways, creative ways, that can be adopted by real systems going into the future. And I would recommend doing that. I would recommend exploring that path, even though you're just beginning your computer science careers, since this is a bachelor's level course. It's the end of a bachelor's level course. I don't think there's anything that prevents you from doing that if you have the desire to do so. Especially right now, you have the background also to innovate potentially. Of course, you need to digest the material a little bit, and it may take some time to do the digestion, but never underestimate yourself in the sense that you can come up with big ideas that can change the world. So as I mentioned in the last lecture, I would recommend following your passion, getting good guidance while following your passion, because hopefully your passion needs to be well guided as well, so that it can solve a big problem. But along the way, you need to be resilient, because in all cases, you will get pushback from people who don't understand the ideas, from people who don't care about it, et cetera, et cetera. There are many reasons to push back on new ideas. And many people do that, unfortunately. Sometimes it's fortunately, sometimes it's good pushback, sometimes it's bad pushback, but don't be derailed by it. And this is an important advice that I give you based on my experience in the past, because if you get derailed, and if you don't follow your passion, then you may actually lose out, and the world may lose out on the new ideas that you can develop. So you need to, I think, relentlessly follow your passion if you're passionate about something. And it's good to be passionate about something when you're trying to solve problems. And I think building infrastructure to enable your passion is good. We have done it with RowHammer, for example. We're doing it with processing in memory. We're doing it with many research that we do. So building infrastructure takes time. There's a saying that big ideas or research is 99% sweat to get the 1% pearl. So you want the pearl, which is important and which is going to change everything. And you have to give 99% sweat, 99% of the time. You can make that 99.99% if you want, which is perfectly fine, I think. So basically, I think this build infrastructure can be rephrased as work hard, because if you want to enable something big, you need to work hard. Well, of course, you need to be principled as well, but there's no big idea that's been enabled without working hard that I know of. So I think that also requires resilience, right? So be resilient, I think, is important. And I think focus on learning and scholarship. There are a lot of things people focus on these days, even in research and scientific community, that I think are essentially anti-science. The focus really should be on what have I learned, how have I advanced the state of the art and the future, and how have I contributed to the scholarship of the world collectively. Those are the only things that really, really matter for your impact. Everything else is just noise plus bureaucracy, let's say. So I think learning and scholarship is really important, and make that the compass in your careers, I would say. And in the end, I strongly believe in this, the quality of your work defines your impact, and nothing else in the end. You have to make it high quality. Of course, there needs to be a good idea, etc. And your passion needs to lead to something big, right? But in the end, it has to be high quality to have impact. If it's low quality, then maybe you should not do it in the first place, right? And I think overall, you can make a good impact on the world, assuming you have a good mindset, good goals, and good focus going into the future. And I strongly believe in this. And I think this is, it's really important for future generations also to believe in this. And I think in the end, it all boils down to this good mindset, goals, and focus. Okay, recall this versus that, right? I think all of these that I just discussed right now, I also discussed in the last lecture, kind of point out to some people who've changed the world, right? We discussed Calatrava, for example, and a key question we asked was, how was Calatrava able to design especially ski buildings? And we said, I think I didn't use the word passion over here, but passion is one of them for sure. But hard work, perseverance, dedication, etc., and a lot of other things that he has combined over decades and decades. And of course, principled design and strong understanding and commitment to fundamentals should not be understated ever. And I think, as I said, you will be exposed to and hopefully develop and enhance many of these skills in this course. And hopefully you have seen some of them. And if you do not fully appreciate it right now, but maybe you can take a look back and try to analyze what you have learned based on what we have discussed in the first couple of lectures in terms of design mindset and how to make a difference. Okay, so with that, also I would recommend going to the Calatrava buildings and enjoying them. You may find the closest buildings around the ETH and University of Zurich, for example. Okay, so let me talk a little bit about processing in memory. This is going to be also the subject of the optional assignment that you're supposed to review. So you'll see part of that over here. But I will give you another example thing that we're working on in my group. We're working on a lot of things that we're passionate about. This is one thing that I selected. Clearly, RowHammer I talked about many times. I don't want to talk about it again. But processing in memory, we did not talk about a lot, even though I mentioned it multiple times. But this is something that we're really passionate about. And in my opinion, hopefully when I'm teaching this course next time, I will show more and more of these processing in memory systems. And maybe if I teach this course 10 years down the road, or some other course 10 years down the road, maybe we will be talking about processing in memory-based systems in a good fraction of the course. That's what we would like to hope. And that's what we would like to enable also. But you already know that data access from memory is the major performance energy bottleneck. We've seen this in many different ways. When we motivated the memory, the memory problem and when we started studying memory, I'm going to show you some of those slides again. But basically, to critically think, if we do some critical thinking, we will quickly figure out that our current design principles cause great energy waste. Why? We're basically moving data all around the system. To access some memory location, we have to go through, to operate on some data, we need to bring the data into the processor. And that's clearly costly in terms of energy. That clearly costs us performance. We tried very hard to avoid that performance loss, right? We just discussed many caching, prefetching mechanisms to avoid the latency of a memory access. That complicates our system greatly. We've just seen virtual memory. We've just seen all of the aspects of virtual memory tables, TLBs, TLB hierarchies, page walkers. This is just to do the translation, not even to get the data, right? This is just to do the translation to access the data. Same thing happens with data access also, basically. We build hierarchies and hierarchies to tolerate the performance loss. that caused even more energy waste. So right now we are in a vicious cycle, I will say. In this cycle, data access is causing a lot of problems to us, wasting a lot of energy. It's causing a lot of performance problems. To avoid the performance problems, we're building huge memory hierarchies, huge prefetchers, et cetera, multi-threaded engines, et cetera. They're causing even more energy waste in our system. And we cannot break out of this vicious cycle. So how do we actually break out of this vicious cycle? Well, we need to do something different. And a critical thinker would say, why don't you process the data where the data is? Don't move the data, basically. And that's the subject of processing in memory. Do not move the data. Somebody should probably call it do not move the data engine, right? And if you look at the components that I showed you earlier in this course, we talked about computation a lot. We talked about communication a little bit. We talked about memory a lot in the last lectures. But we were very computing centric throughout the course because existing systems are overwhelmingly processor centric because that's the only place you can do computation. And computing unit includes the accelerators like GPUs today, machine learning accelerators, same thing basically. Memory is far away. Computing unit is heavily optimized. All data is processed in the processor at great system cost, as we have discussed. Processor is heavily optimized, considered the master. Everything else is dumb and largely unoptimized. So the question is this the right way of building the system? And I think based on what we have seen so far and based on this questioning that I have provided to you, probably you're ready to answer no, because you have seen these slides before, right? You've seen that we talked about Dick Seitz, who designed the Alpha processor with his team and said that memory is the biggest problem we're having. We designed this processor. It's running at 1/20th almost of its peak bandwidth. It's not finishing 4 instructions per cycle. Forget about it. It's finishing 1 instruction every 5 cycles almost. So why? It's waiting for memory. You've seen this slide multiple times in run-ahead execution also, right? In prefetching. Most of the time, the processor is waiting for memory. You've seen this slide from a Google paper where they analyzed all of their data center workloads, and they basically say the same thing. Most of the time, the processor is waiting for memory. It's not just waiting for memory, it's accessing memory, it's moving data from memory, it's wasting energy also. So basically, because we have this fundamental choice in the designs that we have in systems today, everything is processor-centric. As a result, we have grossly imbalanced systems. Processing isn't done in only one place, everything else moves and stores data. This is energy inefficient, low performance, and complex. As a result, we have an overly complex and bloated processor and system overall, as we have seen in the memory hierarchy. And this is energy inefficient, low performance, and complex as well. As a result, I've shown you this picture at some point. Most of the system is dedicated to storing and moving data. We call this a computing system, but most of the time it's moving and storing data. Actually, you've seen a lot of pictures. I haven't replicated them over here, but you've seen a lot of pictures in real systems. Most of the system is cached. More than 60% of an entire die is cached. And AMD is adding, as I showed you earlier, even more cache into the system, right? That's true for all companies, not just AMD. I picked on it because they announced this 3D stack cache, right? Okay, so maybe we're doing something fundamentally not right at this point. So, okay, data movement versus computation energy. You've also seen the slide. Basically, today, a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition. So does it really make sense to move the data into the processor? And we've said that 70 years ago, this was not the case. Over time, logic scaling, technology scaling helped the performance and energy of logic gates. It didn't help the energy of the interconnect and performance of the interconnect. As a result, logic gates became much more energy efficient and faster. Interconnects stayed as slow and as energy efficient as before. They scaled a little bit, but not that much. As a result, 70 years ago, a double precision floating point operation was expensive, or even just a simple add was expensive. Memory access was less expensive, but 70 years of technology scaling made memory access much more expensive. So we're still designing systems in a processor-centric way, and that's probably not a good idea going forward. And I've also given you this picture earlier. This is a study that we did together with Google a few years ago, where we analyzed important workloads like machine learning, Chrome browser, and video encoding and decoding. And we saw that more than 60% of the total system energy is spent on data movement across the system. And that's probably not a good idea. So basically, we do not want to move data. Then the question is, how do we design a system that does not move the data, that minimizes data movement? This is a paradigm shift. We want to enable computation with minimal data movement, compute where it makes sense, where data resides. It could be anywhere. It could be memory. It could be disk. It could be tape. It could be where the data is generated in a genomics engine, for example, in a genome sequence analyzer. We want to make computing architectures more data-centric. And the goal is really processing inside memory. This is one place where we can do processing. As we have talked about memory so far, memory is not active, right? It's passive. It just gives you data. Maybe it refreshes itself. Even that, it does it under the direction of a memory controller, right? But we want to shift computation here. And that's why this is a paradigm shift. We want to store our important applications, whatever you can imagine. Machine learning could be part of these, of course. And we want to query the memory, saying, memory, do this function for me. Memory does it, provides the results. Today, we don't have the capability or the interfaces to do this. There are many questions over here. How do we design the compute-capable memory and the controllers? How do we design the processor chip and the in-memory units after this? How do we design the software and hardware interface to enable this? How do we design the programming languages, compilers, and system software to enable this? How do we design our algorithms and map them to the in-memory processing substrate over here? And how do we actually think the theoretical foundations of computing? So this is an across-the-stack problem going all the way from devices that can compute, logic that can enable computation, microarchitectures that can enable computation, interfaces that can enable pushing of computation to memory, system software, languages, algorithms that can enable this. Theoretical foundations, I will also talk about this. At some point in your career, you will take a theory of computing science course, theoretical computer science course. Maybe you're taking some of it right now. And you may learn about big O notation, for example. And if you look at the theory of computing science, it's very processor-centric. It assumes that processor is the thing that processes the data. And as a result, you count operations. Big O notation is all about complexity of algorithms, analysis of algorithms. You may be taking these courses at some point, is all about counting the operations. It's not about counting data movements. It's not about the memory at all. It's really about how many operations that you do. That's it. But if memory is the most expensive thing, is that really the right way of analyzing systems? And is that really the right way of building systems going into the future? So even the theoretical foundations of computing is ingrained with a very processor-centric mindset, if you will. And going forward, that may need to change. Even theoretical foundations of computing may be critically thought so that we have a more data-centric mindset. Okay, so processing in memory actually is a very rich field today. It's not a new idea. It was proposed in late 1960s for the first time. But today it's becoming a lot more important. And because we have a lot of issues in technology, applications, everything we talk about related to the memory system. And there are two approaches to it. I'm going to very quickly talk about them. And then I'm going to show you some example research going into the future. Processing using memory is a very interesting approach. It really uses the underlying memory substrate to do analog operations. So actually processing near memory essentially puts some logic near memory. It doesn't use the memory cells themselves to do analog operations, but it's really put some logic near memory. So it's very similar to what we have today, except processors are much more tightly integrated with the memory. For example, you may have a pipeline processor near a bank. You may have a pipeline processor inside the logic layer of 3D stacked memories, as we will see, similarly to what AMD has done, for example, with some differences, of course. So basically, both processing using and near memory view memory as an accelerator. So essentially, you have some specialized or general purpose compute capability in memory. You use that compute capability, and we know how to build a lot of accelerators in our system today, right? The difference in the memory side accelerator is that it's not bottlenecked by the memory bus. It's not bottlenecked by the cache hierarchy. It has direct access to huge amounts of storage at high bandwidth, low latency, low energy. That's why this accelerator is potentially very precious. Then, of course, how do you design that accelerator? Maybe it's a general purpose core also, right? So memory is similar to a conventional accelerator. So let me give you one example from our research. Basically, we showed that you can do in-DRAM copy, zeroing, or initialization, and or not and majority operations at low cost using analog computation capability of DRAM. And the idea is, remember the rows, you activate rows, just like in RowHammer. If you activate 3 rows concurrently, you perform computation, analog computation, which leads to bitwise AND or NOT and majority functions, which are functionally complete, as you know from this course, which means that you can map any program onto the substrate that you can do in DRAM. And we showed that you can actually have significant performance energy improvements, 30 to 74x in this paper. If you're interested, you can take a look, of course. And new memory technologies enable even more opportunities. These are memory technologies like phase change memory, memristors, etc., because they actually are non-volatile. As a result, the data movement is even less. So if you want to know more about this, certainly you can read the papers we have written on this topic. This is a more recent paper that has a good DRAM background also, actually, that I mentioned earlier. And this is one of the more recent papers that we've written on this topic. You can see that the paper is titled SIMDRAM, concepts that you learned in this course. Basically, we can do bit serial SIMD processing using DRAM in this particular work. Okay, there are other very exciting things that you can do in DRAM or memories in general. For example, you can generate physical unclonable functions, signatures in memory. I'm not going to talk about how you do that, but these are important for security of systems, clearly. If you have in-memory computation, you should have security substrates over there on the memory side as well. If you can do a true random number generation in DRAM, and this is one paper that we've written on this topic, and other papers coming up next week. It's already on arXiv, actually. You can take a look. So certainly you can do a lot of interesting things inside the memory chip, just using the analog operational principles of memory without adding any logic. Okay, but there's another opportunity that you can exploit, which is the 3D stack logic plus memory, which AMD exploited in their caches, for example. And the idea over here is you have memory layers, and then you have a logic layer, and then you put memory layers on top of a logic layer, and you have 3 silicon vias to connect them, just like in the AMD processor earlier. Now you have reasonably tight integration between memory and logic. The good thing is the memory and logic is fabricated in different ways. As a result, the logic can be good quality also, but there are a lot of technology issues over here. Going forward, there are monolithic or true 3-dimensional technologies that are under development. But now you can put anything into this logic layer. Any idea that we have discussed, any processor organization that we've discussed in this course can be inside the logic layer. Now you're very close to memory, right? This is processing near memory, basically. And we have also done a lot of work in this area. We're still doing work I'm going to show you, but this is one example of the work. I'm not going to go into the details of it, but this is an accelerator for graph processing. Graph processing is very important in many applications like genomics, machine learning, etc. today. And we can actually accelerate graph processing using a processing in memory engine, near memory engine that looks like this here. Here we have one memory plus logic chip. And inside it, we have many in-order cores over here. And you don't move the data here. You basically move the computation to the data. Basically, whenever you want to update a graph node, for example, you ship the computation to the graph node that is housed by the particular memory layer that's on top of a core. So you partition your data within this 3D stacked system. And of course, to scale up, you certainly need to have many of these systems interconnected, many of these chips interconnected with each other. And you can essentially do the computation across them with minimal movement of data. And with whenever you want to update something, you basically ship the function to the computation. So essentially, function to the data, sorry. So communication, essentially, this is very much like a distributed systems programming, remote function call-based programming, and hardware supports that remote function-based call-based programming. And there's prefetching mechanisms internally so that you can exploit the high memory bandwidth that you have over here. So this is beautiful, I think. It basically shows that you can do computation near memory, and you can change your programming model to enable that computation. And the benefits are significant. So when we evaluated this system in 2015, it's right now relatively old, but a lot of work has built on the system, actually. And people have shown even better results than us right now because they optimize the system. You can see that these are existing systems. What do they have in common? In common, memory and processor are different from each other. There's a dichotomy between memory and processor. Processor is here, memories are here. That's the difference. These are different types of memories, hybrid memory cube, DDR3, different types of memories. And the bandwidth is limited. Why? Because you're going off chip to go to the memory. Tesseract, which is our system that I showed you in the earlier picture, looks different. Basically, there's no dichotomy between processor and memory because they're tightly integrated with each other. Each of these is a 3D stacked chip with memory and logic in it. And the overall bandwidth that's exposed to 512 in-order cores, just like here, is 8 terabytes per second. It's more than an order of magnitude compared to the best system that we had at the time. And the benefits are commensurate. Basically, on 5 important graph processing algorithms, the performance improvement you get is more than 13x, according to our results, even without optimizing the system. And the energy improvement, and because you can exploit very high levels of memory bandwidth, and the energy improvement is also commensurate, it's more than 8x. Basically, there's significant improvement. And other later works actually show that you can increase this performance improvement with better system management, new ideas, to almost 100x on graph processing. And the energy reduction is also commensurate, which is about 100x I don't know the exact numbers, but it's close to 2 orders of magnitude, essentially. And if you're interested, this is a work that has had a lot of influence in the field. This is not the first work on 3D stacked memory, but this is the first work that showed that you can get high speed ups by customizing a processing in memory system for graph processing acceleration, essentially. And clearly there's more work after this because it's 2015, right? So one of the important questions that we tackle is how do you enable adoption of processing in memory? Because you built this new hardware, and this is a new execution paradigm. Adoption is always an issue, right? As we discussed in this course, and as you're very well aware, whenever you change the interface, whenever you change something that has to change the software, you will have difficult adoption issues. And many people failed in the past. Even big companies like Intel, for example, whenever they wanted to change the instruction set architecture to something completely different, they couldn't, because software base needed to move and they had competition. Maybe if software base needed to move was the only thing and they didn't have competition, then they could have succeeded potentially, right, by causing a lot of pain to all of the software programs in the world. But they did have competition, so it's very hard to move the software base by changing the system completely. So processing in memory is a different way of thinking about how to design systems. It's a different computing paradigm. So it always have it as adoption issue. So there are adoption issues that we tackle, like what is the functionality that you want to put? What are the applications? What are the software? What is the software like for processing in memory? How do you ease programming? How do you provide compiler and hardware support interfaces? How do you provide system support like coherence and virtual memory? These become issues in processing in memory as well. It becomes even worse in processing in memory, actually, both of them. Runtime and compilation systems. How do you design such systems to make life easier for the programmer? Data mapping, access and sharing control, protection, scheduling, etc. Everything that needs to be rethought for data-centric systems like processing in memory. And how do you design infrastructures to understand the benefits and feasibility and develop all of this? So there are a lot of questions here. And I think all of them need to be tackled, and we're tackling them. Multiple other people are tackling them. And all of them need to be solved with a change of mindset, because the benefits of enabling a processing in memory system is huge. You get significant performance and energy improvements. Your systems become more sustainable going into the future. And you basically don't violate the balanced design principle. Remember, we talked about microarchitecture design principles, critical path principle, balanced design principle, bread and butter principle. Processor-centric designs actually violates almost all of them. Maybe critical path, you can argue, but certainly bread and butter. Common operations like memory accesses are handled terribly in a processor-centric system. That's the bread and butter design, optimized for the common case. Remember the microarchitecture design principles. Balanced system design principle is destroyed in a processor-centric system because the system is not balanced. Everything just stays idle or just serves the processor, and that's it, right? So basically, we're violating a lot of principles, and we need to change our mindset so that we actually have much better and much more principled designs going into the future. So basically, we need to revisit the entire stack if we want to change the computing paradigm to a more data-centric paradigm, and we can get there step by step. So this is a huge challenge and opportunity for the future. How do we design computing architectures with minimal data movement, which will lead to fundamentally energy efficient architectures, and that requires data-centric designs, and also fundamentally high performance architectures, because that also requires data-centric designs. Okay, so the talk I mentioned, Intelligent Architecture for Intelligent Memory, that you are welcome to review for 1% credit, is going to be about this in a little bit more detail. But if you want to learn more about processing in memory, we've written this survey paper, an overview paper that describes processing in memory, that also gives you a lot of history about why things are different today in enabling processing in memory. So if you're interested, you can actually read about this as well, or watch the longer talks that I mentioned. And there are other review papers that we have written that focus on different aspects of processing in memory. This was, for example, published in IBM Journal of Research and Development in their special issue for hardware for artificial intelligence. It's already appeared, actually. It's this stale wording over here. But you can also take a look at these other papers. And as I mentioned in earlier lectures, processing in memory systems are real right now. They're real systems. This is one example of a real system, UpMem system. It's a company in Grenoble, France, very close to Switzerland. And we work with them quite a bit, actually. And what they've done is essentially in a DRAM chip, they've added processors. And what does this mean? They call it DPUs, DRAM processing units. And Now you know the internal organization of a DRAM chip. You have multiple banks, right? Here in each bank, you have a processor. I'm going to show you a picture of it in a little bit. In each bank, you have a general purpose processor with a 14-stage pipeline, I believe, if I remember correctly, and you can execute code on it. So essentially, this is an example of processing near memory. You basically have a processor near memory that you can offload code to, and you can program these systems. We have programmed these systems in our lab, and I'm going to show you a paper that you can read if you're interested. But these are real memory modules right now, very similar to your other memory modules, except these are processing capable memory modules. And I think this is fascinating. This was introduced in 2019, and you can read a lot more about their performance analysis right now. And you can see the newer version, P21 version, you can see that it has more chips. DPUs are faster. You can see one of the disadvantages of putting a DPU or processing unit inside a DRAM chip. As I said, DRAM is fabricated very differently from processing logic. It's really optimized for low leakage for the capacitor. And this goes against designing very fast transistors. And you can see this in the frequencies of the DRAM processing units that they have. Fundamentally, they're limited to smaller frequencies because inside the DRAM fabrication process, it's very, very difficult to get a 4 gigahertz processor, let alone 4. Maybe not even 1 gigahertz processor, right? So it remains to be seen. But the good thing is people are trying. So the benefit comes from not high frequency design over here. The benefit comes from the fact that processor is tightly coupled with memory. You're not moving data off the DRAM chip. As a result, you're doing processing right where data is. You're saving energy, you're saving latency, you're saving performance, you're saving a lot of things. And you can do this in parallel across all of the banks. This actually has 2,560 processors if in a 40 rank system. So basically, you have a lot of capability for processing, assuming you can map your application and data nicely to the system. The benefit you're getting is not from frequency here. So you need to change the mindset also when you actually think about how to program these systems and how to take advantage of them. The benefit really comes from minimizing the data movements. And this is another maybe more beautiful picture, if you will, that is in a paper that I'm going to reference next. It basically shows that this UPMEM system in action, if you will. It has PIM-enabled memory. It also has DRAM. And PIM-enabled memory is hopefully where you offload a lot of your computation so that you don't move data between CPU and either PIM-enabled memory and DRAM. And you can see that this has 20 memory modules of 16 chips each. There are 40 ranks in total. Now you know all this terminology, hopefully. And overall, there are 2,560 DPUs. So it's a highly parallel system. It's a highly distributed system within a node, as you can see over here. And you need to program it nicely to get the benefits. And if you're interested more about this, we have lectures. Juan gave a lecture last year in our computer architecture class. If you're interested, take the computer architecture class also. But this lecture you can watch if you have interest. You can see that this is the internals of a DRAM chip, actually a DRAM bank. Each DRAM bank, there are 8 DRAM banks over here, as you can see. Each DRAM bank is coupled with a processor. And you can see the pipeline. The pipeline looks kind of like the pipeline that we have seen, except it's a bit longer. And there's some instruction memory, there's some data memory, and there's some data movement engine so that you can move the data. So you still exploit locality. So a lot of the principles that we have discussed apply to this processor that they have constructed. Now, I'm not suggesting this is the best way to construct a processing in memory system, but this is one way of constructing the processing in memory system without changing the programming model a lot. And even this leads to significant performance improvements compared to existing CPUs and GPUs. And you can read about that in this paper. This paper that we wrote recently, you can find on arXiv. It was published on arXiv last month, actually, in May, in late May. And you can find out that there's a significant effort in analyzing the performance of the system here. And we compare it to, in the end, to existing CPUs and GPUs. And for workloads that are suitable for the system, and we talk about what makes the workload suitable for the system, in those workloads, there are orders of magnitude performance improvement compared to a CPU, and there are factors of improvement compared to a GPU, a state-of-the-art GPU. And there are probably benefits compared to a state-of-the-art GPU in terms of cost potentially. And you can read the paper for more details. So this is a very active area. As you can see, this is a cutting-edge paper on the topic. But there are other active areas in processing in memory. on simulated systems. We also do work on simulated systems. This is another work that we have released. Again, on arXiv, you can find it freely available to anyone in the world. And here we talk about what makes a workload suitable or not suitable for different processing in memory systems. We also analyze caching. We also analyze prefetching a little bit in this particular work. And we categorize workloads. So there are actually more than 300 workloads that are categorized in this work. And we basically provide a data movement benchmark suite. Geraldo is right now working on actually open sourcing it completely. So you can even find the data movement workload suite open source soon. That's true for the workload suite that we develop to test the UpMem systems as well. Juan is doing that as well. But basically, there are really interesting things that you can do to understand why processing in memory works, when it works, how it works, and how to make it better, basically going forward. And today is the right time to do this research going into the future, because these systems need to be enabled. Okay, and the good news is industry is paying even more attention as these works start popping up and becoming more and more important. Industry is paying more attention. I mentioned this. This is at the beginning of the course. Remember, this was actually introduced in on February 17th with a press release by Samsung. And basically, they're doing something similar in the sense that they have specialized units to accelerate matrix multiplication operations, let's say. And they do these operations very close to each bank in memory. And they call this, I think, FIM-DRAM, function in memory DRAM. Don't quote me on that exact name. It's called FIM-DRAM. I think it's function memory. Yeah, you can see that it's a function memory DRAM. And you can see that there's a 3D stacked architecture over here, high bandwidth memory, very similar to what we have seen earlier in my picture. And you can see that they're adding some multiply, accumulate instructions to be executed, offloaded to the memory side. And you can see that this is a real design, etc. I'm not going to go over it, but the good news is that real companies, big companies like Samsung, are now finally paying attention to this. Clearly, processing in memory is an old idea, started in the 1960s. When we first started working on it, it was 2011 or so. Now, finally, people are paying attention in industry, and that's a good thing, basically. The question is, of course, how will it evolve? And you can have a big say, basically, if you actually come up with good ideas going into the future. Okay, so if you're interested in processing in memory, I would recommend detailed lectures. There are many detailed lectures. And if you're interested in it, I would recommend a longer version, but an older version, as you can see, of the talk that I assigned as optional assignment. And you can find this talk over here. So one thing that I will mention is processing in memory, processing inside the device, minimizing the data movement is really important for applications that are operating at the edge, like devices like this. This is a genome sequence analysis device. You may remember it from the lecture, first lecture. And today, we don't have enough processing capability inside this device. We have to move the data out of the device. But processing in memory, processing where the data resides, is a mindset to minimize data movement in the system. And if you really want to exploit the capabilities of these devices so that we can actually do real-time analysis. For example, we give this device to a doctor, and the doctor, in a critical condition, wants to quickly get an indication of whether this patient will react positively to this drug based on their genetic disposition, plus everything else the doctor knows. And they need this information. You need to do fast genome sequence analysis, and you need to do some matching of a database, for example, with the characteristics that you find based on the genome analysis of this patient, so that you can make a judgment call on whether what kind of drug does this patient react positively to, or does not react negatively to. And this is a life or death situation potentially, right? So you need real-time, fast analysis. And there may be less dramatic situations than what I described, but you still want analysis quickly so that you can move to the next phase of treatment relatively quickly. You don't want to wait 2 weeks to get the analysis results in a genome sequencer. And in some cases today, it takes 2 weeks, actually. It depends on what kind of resources you get, etc., and how much money you pay also. But we want this decision to be made in 1 minute or less. And today, we don't have the capability to do that. That's why I think moving data and not having enough processing power where the data is generated is a big problem. In this kind of sequencing engine, if you want to have real-time decision-making capabilities, you really would like to be able to not move the data and have processing capability over here. That's why I think processing in memory can enable new platforms like genome sequencing platforms, medical platforms, scientific platforms, etc., that can give you results in real time and much more efficiently. And we've been working on that also for a while. This is one of the papers that we have written along the way, but we've been working on it since 2011 or so, actually earlier, 2007 or so. And today, actually, we have the devices that are capable of sequencing genomes with very small form factors like this, but they're not capable of processing data. Even your cell phone is not capable of efficiently processing data. Even a data center engine is not capable of efficiently processing data. So we need to rethink how we design our systems. And if you're interested in this, we have written this survey paper. I mentioned this in an earlier lecture also, but maybe it'll become more clear right now. We're working on exciting genome analysis a lot, and I would recommend looking at this paper, examining this paper, if you're interested in this direction. And I think this is fascinating because we can enable new applications this way and new system designs this way. And if you're interested, you can also watch this lecture, relatively recent lecture, where I talk about accelerating genome analysis and our journey in this. And there are a lot of interesting algorithmic issues also that we cover, but a lot of interesting hardware issues that also we cover over here. Okay, there are detailed lectures you can also watch if you would like. But certainly, let's conclude. I think I've given you a lot about some future-looking research. None of this you're responsible for, of course, in the exam or anything. But this is just a foreshadowing of the things that may come about maybe 10 years down the road when you take this lecture, right? Or when you look back into the field. And if you want more of this sooner, there are multiple future options after this course. We offer a bachelor seminar in computer architecture every fall and spring. And you can find web pages for all of these. They're reasonably structured. And in the bachelor seminar, I'm going to talk a little bit more about this, but we delve into particular papers and critically analyze papers, critically present papers, do brainstorming and discussion about papers. So a lot of trade-off analysis goes into it. And this is a fun seminar. We had the last seminar yesterday. It was actually live streamed. You can find some of the publicly available seminars online, and past students who have enjoyed the digital design and computer architecture course have taken bachelor seminar courses, and some of them actually are working with my research group right now, doing either semester projects, internships, experiencing an environment where they can be part of a vibrant cutting edge group. Some of them are doing bachelor's thesis, some of them are doing master's thesis. So those are also options. But I would definitely recommend taking the bachelor seminar because that will give you a different set of skills than we have seen in this course. You will present a paper, you will critically analyze it, and you will lead a discussion about it, for example. I would also recommend taking the master's level course. This is offered every fall. It's a very project-oriented course, as we will see in a little bit. There are 5 labs. One of them is optional, and they're done in high-level language, C language, and it's fun, I think. But we're going to talk about that. And we cover a lot of more cutting-edge issues and more issues that we did not get a chance to cover in this course, clearly. You can also take, that should not be take out, I guess take our, let's say. There are also project and seminar courses that we offer every fall and spring. I have a more detailed slide related to this. If you're interested, you can also take that. And independently or together with any of these, you can decide to do research with me and my research group. As I said, we have a lot of opportunities, and I very much look forward to working with undergraduate students who are excited about doing solving important problems and who may want to have a fresh perspective to these things. I was one of them, actually, when I was doing my undergraduate degree. I did research in different labs and eventually decided to do my PhD. Certainly, this is possible as well. So you can look at our research group webpage on more about what we do, but I've given you a glimpse of it during some of these lectures, as you can see. Okay, and you can learn more about our research group. You've seen, well, at least virtually, you've seen some of the TAs. This is an earlier version of it. And you can actually read our newsletters. This is a January 2021 newsletter where we talk about some of the things that has happened in the last 1.5 years in the group. And hopefully it's interesting. It will be interesting to you. And this is the group motto designed by some of my students. And I guess this is a more newer version of this. Well, this is a newer version of this picture, let's say, that is more reflecting of the times. And hopefully we will not just have Zoom meetings going into the future. That's true, hopefully, for the bachelor's course that we're having right now. In the future, hopefully, we'll have a lot more physical lectures. That will be a different experience, in my opinion, because I don't know what you think, but I don't think this remote experience is the greatest experience because I cannot see the faces of any of my students who are in the class. And that's a bit frustrating, frankly, from my perspective, because, and also we don't have the interaction that we have clearly because you're writing your questions and I'm trying to read them, etc. So it's a different kind of interaction, which is not necessarily great. But you can read our newsletter also, as you can see over here, to get to know more about our research. And this is a little bit more about the bachelor seminar in computer architecture. Basically, it's a rigorous seminar on fundamental and cutting edge topics in computer architecture. You get to critically present, review, and discuss major works in computer architecture. You can cover many ideas, usually with anywhere between 16 to 25 papers or so, something like that. Analyze their trade-offs, perform critical thinking, discussion, and brainstorming. Of course, you don't have to read every single one. You have to read the one, analyze the one you're presenting in a very detailed way. And there's participation, presentation, synthesis report, and you can also register for the course online if you're interested. And I'd recommend taking it if you're excited about it, because you have the background to do it right now, because you have a basic computer architecture course right now. And then there's a master's level computer architecture course. As I said, it covers many cutting edge topics in memory, interconnects, multiprocessors, heterogeneous systems, PIM, processing in memory, and more. Many topics we could not cover in this course. It consists of lab assignments, which is actually very important because it's about 50% of the grade, I think. We wanted to make it more hands-on and lab-oriented, some homeworks and exam. And you can also find more information. You can actually watch videos. A lot of the videos I recommended to you are coming from that course. And finally, these are the projects and seminar courses. These are offered every fall and spring. These consist of short lectures and hands-on projects, which is important. It's a lightweight. These are lightweight but deep courses on specific topics you can choose from. For example, you can choose from topics in memory, and we can define the project together. If you have ideas, we're open to ideas. There are two courses related to memory. Storage, which is something we did not talk about as much. You can also choose them. For example, if you want to do some project on phase change memory or SSDs, it's possible. Heterogeneous computing, both programming and architectural aspects, GPUs, FPGAs, processing in memory. There are two courses related to this, and there's a lot of exciting research that goes on. You can program the UpMem computer, for example, or you can program FPGAs, for example. And finally, more application-oriented, but still hardware, software, co-design type of courses, and some of them actually just algorithm. You can actually develop algorithms to do better bioinformatics and machine learning as well. So these are the two courses over here. So there's one question: aren't PNS courses only for ETH students? So from my perspective, no. I don't think there's anything that limits. So if you have a problem registering, just let me know. I'm happy to take courses from, take students from any department. So because I think in the end it's a learning experience. It's a requirement for ETH students. So meaning, as if you're an ETH bachelor student, that means that you're required to take some number of PNS courses. That's for sure. If you're a computer science student, you're required to take a seminar course. I don't know if PNS courses satisfy the seminar requirement. That's good to check from your perspective. But I don't think if you want to take the course, there's nothing that prevents you from taking the course, as far as I know. And if you run into an issue and if you want to take the course, let me know, because I don't have a problem. If people are excited about taking the course, I'm happy to get them admitted in some way. But again, you may, depending on what the computer science department decided, and I don't remember, frankly, what that decision is, you may not be able to count this as one of your seminar requirements. That I don't know. But you may be able to count it for some other requirement. That, again, maybe there's some room for counting it for something else. That I don't know also. That's probably better discussed with the CS department. But if you need help at any point in the process, let me know. Okay, so I think I've covered the 4 different courses that we're offering in PNS courses. And again, if you have questions, let us know. And you can find the description of the courses and some of the lectures that we presented online as well. But we don't put out all the lectures right now. We're going to put out more lectures related to them, but we didn't do that yet. Okay, so doing research, if you're interested in learning more and doing research in computer architecture, I have 3 suggestions. I've actually presented the slide right before the systolic arrays lecture also. Feel free to email me with your interest. Please CC Juan. My email tends to be, unfortunately, extremely unreliable. I get too much email. Maybe I have, essentially, I'm not operating in a very good point in my email latency curve, let's say. The load of emails is too much in a sense. So if you CC other TAs that you're familiar with, Juan being a primary one, that's a very good idea. Because if I forget, hopefully they will not forget. And you're also always welcome to email again or find me in different ways as well. And I would also recommend taking the seminar course or the computer architecture course. That goes without saying. And if you're interested, hopefully you're doing some readings and assignments on your own. And I know some people in the past have done a lot of readings and assignments on their own. And as I mentioned, there are many exciting projects and research positions, memory systems. And I'm not going to go through this again, basically. I've already said this. And we've covered a lot of really interesting things in the lectures. And a limited list of project topics is in this thesis page, but don't take this as a comprehensive list. Basically, my group works on all aspects of computer architecture and a lot of the topics that we discussed. Thesis topics may be some things that we have envisioned, but you can also define your thesis topic if you work with us. And we may also have other thesis topics that are not exposed on our webpage as well for various reasons. Just one reason is there's just not enough time while doing research to write up a thesis topic online. But if you're interested in architecture, definitely get in touch with us. And again, I think this is a guideline of how to do projects with us. The biggest part is be excited about the topics that we work on and be excited about generally in computer architecture. Have a good mindset. Everything that I said earlier applies. Have good goals and get in touch with me and my students postdocs. And you can do other things over here. Hopefully you've taken our course and enjoyed it, one of them at least. You can browse the projects, read our papers, and get in touch with the authors. Maybe you've done some of that, I don't know. If you're interested, for example, you can read the RowHammer paper, any of the RowHammer papers that we have written. And you can also email us, certainly. And you can also optionally apply. We have a formal application site. But if you're an ETH student, it's easier to contact us, especially if you have taken our courses. You have a more or less personal relationship with us. But outside students who are not part of ETH, we definitely ask them to apply because we do not know enough about them, right? But if you've taken a course with us, especially the seminar course, we've interacted with you a lot more. In a course like this, the DCA, and very unfortunately, because of the Zoom-based nature of the course, online nature of the course, we do not get to interact much. And the course is huge also. There are many students. But if you take the seminar course, we interact a lot and we get to know you a lot better. And you get to know us a lot better. It goes both ways. And then you don't necessarily need to apply through our official page. But if you're applying from the outside, for example, if you're, I don't know, living in some other country, if you want to do research with us, you should definitely apply and let us know that you've applied. Okay, so I'm going to end this lecture and class with two quotes that I like. Actually, there are more quotes that I like than two, but I think it's good to be concise. Just talk about these two quotes. But before that, I think I will handle this question that I just saw. Okay, this is a question. It's a long question, I see. As a programmer, it means that some people are still here. That's good. This is completely optional part of the course. And if you're still here, that's good. I think that tells me that you're interested. But basically, the question is, as a programmer, we always assume our instructions to run correctly. But if any tiny needed part of the ones we looked at fails, we get wrong results. Are chips nowadays reliable enough that this doesn't really happen? Or are there extensive hardware mechanisms to handle those errors? And if so, how can that be done? It's an excellent question. And I think the answer is we don't completely know. Why we don't know? Because sometimes faults happen. And sometimes it's because of hardware problems in the chips. And there's a good fraction of the faults, hardware faults, that lead to some incorrect execution in the programs. It could be RowHammer, one example, right? It could be there's some issue in the ALU that's exercised only under some conditions, some operating conditions, some alignment of the instructions in some way. These things happen, and it's not completely possible to perfectly debug every single hardware component in our systems today because it's complicated. And you saw that we have trillions of transistors, right, in our chips today. So basically, we don't absolutely know. There are some faults that actually lead to crashes, etc. just because they're hardware faults, and you cannot basically blame the software for it. Clearly, there are a lot of faults where you can blame the software. I'm ignoring those, but these are hardware faults. And for example, when I was at Microsoft, there was this study that was being done at that time. I think they eventually published the results. Maybe I'll try to find the publication, where they showed that at that time, Microsoft Windows had the blue screen. I don't know if Microsoft Windows has this blue screen, but this was a famous blue screen. Whenever you get an error, you saw a blue screen and you had to reboot your computer. Nobody wanted the blue screen, clearly. But there was a study that was done at that time that showed that about 10 to 15% of all blue screens are due to some hardware problem, hardware fault. And some of the hardware faults could be preventable. Some of the hardware faults may not be preventable. One way to prevent the hardware faults is, for example, have error correction codes inside the chips. In DRAM, for example, people are adding error correction codes today, but it's not easy or it's not enough to protect against all faults. For example, error correcting codes is not enough to prevent RowHammer type of vulnerabilities, RowHammer type of faults. So it really depends on the type of fault that's happening, the design of the hardware. And some of these faults may not be reliability issues. Some of them may be logical bugs, right? The hardware is designed in some way, and humans are designing it. There could be logical bugs. Some of them could be manufacturing reliability issues. So there are all these different kinds of things. We have analyzed, for example, in a paper that we published in Micro 2008, we have analyzed hardware bugs. And we've seen that the microprocessor errata is increasing. It basically has even more errors that are documented in the instruction manuals, in the architecture manuals, that basically shows that microprocessor designs have increasingly more bugs. And sometimes these are exercised. So I think your question is very to the point. It's very important. There are reliability issues, there are logical bugs, etc. And they're all intermingled when you get an error. And you need to basically tease out what is happening when you get an error. And sometimes it's not easy to do. That said, I think people are doing some studies. Actually, there's a paper from Google in this Hot OS. There's a workshop that has happened. It's called Hot OS, Hot Operating Systems. And Google basically shows in this paper that there are a lot of faults that happen in hardware that lead to basically some corrupt execution in software. I'd recommend finding it out. And hopefully my TAs who are listening will find out right now. You can feel free to put it on the chat if you find out. But this just happened a couple of days ago. And these Google folks basically analyzed the hardware and the software that they have. And they showed that there are a lot of hardware faults that cause their software to crash or become corrupt in some way. So these are real, basically, and they're going to become worse going into the future. And essentially, the answer to the second part of your question is, are there extensive hardware mechanisms to handle those errors? And I can confidently say that the answer to that is no. Basically, unfortunately, there are no extensive hardware mechanisms today to handle all types of errors. Some type of errors, for example, memory has error correcting codes, not all memory. Consumer memory in your laptops, for example, don't have error correcting codes. Increasingly, they're going to in the future, but not enough error correcting codes. They can correct, for example, single error corruption. They can detect double errors. Well, not always. In some cases, they can detect double errors, but not always. So they're limited. If you have 3 errors, for example, in memory, you're not going to be able to correct them or even detect them in some cases. So certainly there's a lot more to be done in research as well to understand the causes of these faults and to correct them. But your question is a good critical thinking for sure. Okay, so there's another question. That's good. We were also having probabilistic algorithms this semester. Are ideas of probabilistic speed up or also implemented in hardware apart from ML accelerators? So that's a very good question also. So ML accelerators certainly make that trade-off, right? Basically, so looks like I think one of my students, Max, who's doing research with us, actually posted the Google paper, cores that don't count, and I would recommend looking at that. Thanks, Max. Let me go back to answering the question. So ML accelerators, for example, because things are approximate today, and machine learning by nature is probabilistic, you can cut corners in hardware and not have highly accurate representations of data, for example. And you can basically omit some computation. That's possible. You can make the computation simpler, cheaper. You can, for example, instead of using 32-bit floating point operations, you can use 4-bit integers. In fact, inference engines today use 4-bit integers. That's one way of approximation, for example, And I would maybe if you stretch it, it's not necessarily a probabilistic algorithm, but it's taking advantage of the probabilistic nature of the algorithms that are employed in the machine learning, statistical nature of the machine learning. And certainly machine learning accelerators take advantage of it. As far as I know, in the general purpose domain, this is much harder, right? You need to know your application. And I think there's another place where this is taken advantage of, which is video. For example, when you have a video accelerator, depending on the bandwidth you have to the network, for example, the video accelerator, both software and hardware, can scale how much processing they do to the video, depending on the battery life also. So your video accelerator can work faster or slower. So this is taking advantage of the fact that video is also, I mean, it's sometimes probabilistic from the user's perspective, right? If I don't see every pixel correctly in my screen, I can still make sense of it. Especially when I'm running out of battery, maybe I would prefer my battery to run 1 hour longer than seeing everything perfectly on my screen, right? So you can make this trade-off. So on an application basis, this probabilistic nature of the algorithms and also tolerance of the users to the probabilistic nature can be exploited. And I think machine learning accelerators, video accelerators are the places that I can give you examples of, but this is much harder to do in the general purpose domain, because in general purpose domain, again, you don't know what algorithm in the real true general purpose principle, you don't know what algorithm you're really executing, right? So you cannot customize. But I think increasingly the stochastic or probabilistic sort of acceleration is going to be employed as applications become even more stochastic and stochastic. But again, you cannot really generalize it to all applications. I mean, if you want to generalize to all applications like banking, it's going to be difficult, right? I would prefer that probabilistic nature of the hardware or the algorithm to be in the favor of my bank account. But if it becomes either way, it's going to cause problems. But that's a very good question also. Okay, there's one question that I think is on YouTube. What is your view on analog compute? Are we constraining ourselves by converting everything from analog info to digital and backwards, similar to a process-centric architecture? So this is also an excellent question. And I think, again, we should really be examining very energy efficient forms of computation going into the future. And so far, we've been completely digital, especially in the general purpose computation domains, right? And I think going forward, we do need to think about analog computation. Yes, that was not the case. In the early 50s, 60s, 1960s, 1950s, there were analog computation computers that were designed. But over time, people developed the digital abstraction or became more comfortable with it. And digital abstraction was a lot easier to deal with, of course, because analog is you're operating in the analog domain, right? And while the nature is completely analog, no question about that, it's also subject to noise. Basically, you're very much subject to noise whenever you do some analog computation. And people are moved to digital so that they can avoid these noise type of issues and they can get better precision, let's say. But I think going forward, we do need to re-examine this choice. Maybe we don't go completely analog, but there are cases where we can benefit from analog computation capability to a limited extent. And maybe we do the digital to analog conversion and analog to digital conversion not as often as we do right now, because today everything is converted to digital right away and we operate on the digital domain. And clearly, digital domain is not scaling very well. But if you operate on the analog domain, in fact, you can use the memories for computation. That's what I mentioned earlier when we talked about processing using memory. A lot of the processing using memory work takes advantage of the analog operational principles like chart sharing principles in DRAM, but other analog operational principles like current laws, like Ohm's law, which is an analog law, to really do the computation in the analog domain. And I think people have shown that this is very efficient. The difficulty is whenever you need to convert it to the digital domain, it's at some cost. But if you actually design your system carefully, you can take advantage of both analog and digital. And analog is certainly it also rhymes well, if you will, with the stochastic nature of algorithms today, right? If algorithms are stochastic, and if analog is stochastic, subject to noise, maybe you can get away with it, right? So machine learning, for example, can again benefit from analog computation. But I think analog computation is more general. You can more general purpose because if you can do limited analog computation, limit your error, limit your noise, and you can benefit significantly from the energy efficiency of analog computation, you can have a much better system. So going forward, I think, yes, certainly this is something that needs to be rethought. So somebody on YouTube says analog is useful for AI. Yes, absolutely. And data converters are expensive in terms of power and area. That's absolutely true also. Basically, any sort of conversion that you have, analog to digital, digital to analog, is going to be expensive. But if you actually do it in a judicious way, in careful places, then you can actually get the best of the analog while minimizing the conversions. This is also similar to optical computing, right? We did not talk about optical computing, but that's the subject of, again, future courses, lectures, research. If you have optical transmission, optical interconnects, for example, the question is basically, do you do optical transmission or electrical transmission? And people have shown that optical transmission is very efficient, very high bandwidth. But electrical is how we do things today, right? Today's computers are electrical. They don't do optical computation. People also looked at optical computation as well. There are some overheads. But do you do communication optically and then convert the optical data to electrical data when you want to compute on it? And people have looked at the trade-offs. If you have a very costly optical to electrical and electric to optical converters, there's a danger, right? You do communication optically, and then you need to convert into the electrical domain to do the computation, and then you need to convert it back to the optical domain to do the communication, etc. Then you may actually lose. If you're very careful, maybe you gain. But if you also move the computing to the optical domain, if you have optical computation and replace the electrical transistors, and then actually it becomes interesting as well. But again, that's beyond the subject of this course. And actually, it's a lot of it's subject to research. How do you do the computation optically? Right. Okay, is there research to store information optically? Yes, there's also research to store information in many different ways. Optical is one example. Unfortunately, I mean, they're not completely there yet. So there is storage elements. So certainly we have a lot of good storage in terms of magnetic storage, right? So magnetic storage is great in tapes, for example. Solid state drives are great, but optical storage has not been cost effective yet. But going into the future, again, things can change, right? There are a lot of emerging technologies that people are examining. For example, there's work in Microsoft in Cambridge that tries to store information in glass. Now, it's not clear if this is going to be very fast, but it's going to be very durable. There is also research that tries to store information in DNA, but that's going to be very, very slow unless we are extremely successful in our research, for example, to try to accelerate genomics, so genome analysis. So there are many, many different storage media that people are examining. Unfortunately, none of them are good enough to make a dent in the memory hierarchy today or the storage hierarchy today. They're still subject to research, which is good to do, of course, right? There's also research on quantum that we briefly discussed, which is even further into the future potentially, even though there's a lot of investment into it. Quantum principles are potentially even into the future. And certainly quantum storage is not clear. The current state of research in quantum computing, even quantum computing considers DRAM, for example, as their main memory. And that says something about DRAM and how successful it is, I think, going into the future. How successful our current technologies are, it's very difficult to disrupt them unless you come up with solutions to a lot of the difficult problems that these other technologies have. But that's why they're research. That's why research is very important to do, so that at some point you can disrupt the systems, right? Just like phase change memory disrupted systems. We talked about phase change memory. We talked about the research we have done and research others have done. Our research started from 2007. And we wrote the first paper in 2009 saying we should replace DRAM with phase change memory. And that sort of memory came about only in 2019, right? And this is phase change memory. This is a technology that we knew about a lot in the past. We just needed to make it happen in some way. And that required a lot of device level, circuit level, chip level research, plus architectural level research. But optical, quantum, these are even into the future. Glass, these are even into the future. And DNA, I think, we'll see, I guess. Okay, very good questions. I think I will conclude with these two quotes that I like. As I said, there could be many, many other quotes that can be given, but I will be concise. I like these two quotes. these are from someone who has received the Nobel Literature Prize. You may know this person. But I like this quote because this is nice. The reasonable man adapts himself to the world. The unreasonable one persists in trying to adapt the world to himself. Therefore, all progress depends on the unreasonable man. In a sense, this says basically you should be critical of how things are done and what's happening so that you can actually enable progress. And hopefully, but of course, I think unreasonable man needs to have a good mindset with something good in mind. Unfortunately, there needs to be a moral judgment over here as well, because if the goal of the unreasonable man is to destroy the world, then you have a problem, right? But this is said in a way, assuming goodness of the unreasonable man over here, if you will. So I think this points to the critical thinking. And I think one of the most harmful ways of thinking in the world is this sentence, but it's always been done this way. So basically, just because things are done in some way doesn't mean that that's how they should be done that way, right? There are many reasons why things are done that way, and that's not necessarily the best way. It's all a trade-off in the end, and sometimes the trade-offs become extremely negative to the way things are done. And whenever that happens, you should realize that immediately and change. And this goes well with the other quote from this person. Now I've revealed that person, George Bernard Shaw, who's an Irish playwright and novelist, actually. But this ties in nicely with the second one. Progress is impossible without change. And those who cannot change their minds cannot change anything. And basically, I believe this. If you're too resistant to change, or if you're resistant to change, then you cannot really do anything big. And I hope you as takers of this course will remember these quotes, because I think these tie well with each other. As I said, one of the harmful things that has been against progress has been, oh, but we always have done it this way. And whenever you hear that, you should perhaps be very critical. Oh, but this is the only way to do things. Hopefully this course gave you many, many other examples of different ways of doing things. And that's really the mindset. If you don't take away anything out of this course, I would suggest taking away that mindset. Basically, there are many ways of doing things, and it all depends on the trade-offs. And you need to find the best way of doing things depending on the requirements and the conditions. And be the unreasonable man with a good mindset and be open to change all the time. Okay, and that's how I will conclude. I think there is a lot more in computer architecture that we're not going to cover, and we're already out of time. For those who have stuck around, thanks. But for those who have not, you can also watch this if you're really interested separately. And hopefully your next lectures, next semester in your career is going to be in person so that you can get the benefits of it. But hopefully you can also have the flexibility of watching them online. And we will certainly try to provide the best of both worlds because different approaches work best for different people, as we have discussed in the past. But I think the lack of an in-person classroom, certainly I understand it's not good for many of you. And believe me, it's not good for me also, because I really don't enjoy lecturing to my beloved iMac over here without seeing your faces. But anyway, hopefully we'll change that. But I think you can be the agents for change. Also for that, get vaccinated, hopefully. Okay, I think we're done. Are there any burning questions on anything? I know we're way out of time, but some of you are sticking around, and feel free to ask questions. Okay, I guess I don't hear or see any questions. I think with that, at least we're done with the lectures. Hopefully I will see some of you in person in future semesters, and maybe during the exam, because that is planned to be in person at this time. Don't worry about the exam, worry about learning, and we will be in touch with some material that you can study for the exam as well in the remaining, well, during the summer months. But apart from that, hopefully you will enjoy your summer and you will get some time to rest as well as grow at the same time. Okay, I think we're done. Thank you. Thank you for everyone who's saying thank you. I cannot respond individually, but I can see it right now on the screen. I think good luck with everything. Feel free to contact us. As I said, feel free to email me and the TAs regarding anything that you want to talk about. And we will be in touch regardless about the exam at least. Okay, take care. Have a good summer. And have a good weekend before that, of course.